Imagine a world where every choice you've ever made spawns an infinite number of parallel universes. In one reality, you're listening to this very recording. In another, you've already drifted off to sleep. In yet another, you never pressed play at all. As we embark on this journey through the multiverse of paradoxes, consider the profound implications of your every decision. Are you truly the author of your own destiny, or merely a passenger on an infinite train of possibilities? The answers may be more unsettling than you ever imagined. Picture yourself in a dimly lit room, face to face with a younger version of your grandfather. Your hand trembles as you reach for the pistol in your pocket. How could you have existed to make the journey in the first place? This paradox exposes the intricate web of causality that underpins our understanding of time and challenges our notions of free will and determinism. Consider the implications of this paradox on our perception of time itself. We typically view time as a linear progression of events, each causing the next in a neat, orderly fashion. But the grandfather paradox shatters this comforting illusion, revealing a universe where cause and effect can become tangled in impossible knots. It forces us to question whether our actions in the present moment are truly free, or if they are bound by the immutable chains of past and future events. The concept of causal loops emerges as we grapple with this paradox. Imagine a circle where each point is both the cause and effect of every other point. In the context of the grandfather paradox, your very existence becomes both the reason for and the result of your time-traveling mission. This circular causality challenges our fundamental understanding of how events unfold and interact across the temporal landscape. As we ponder the philosophical ramifications of this paradox, we must ask ourselves, does it conclusively prove the impossibility of time travel, or does it merely expose the limitations of our linear perception of causality? Perhaps our understanding of time is fundamentally flawed, and the universe operates on principles far more complex and counterintuitive than we can currently comprehend. Various resolutions to the grandfather paradox have been proposed over the years, each offering a unique perspective on the nature of time and reality. One such solution involves the concept of branching timelines. In this model, when you travel back in time and alter the past, you create a new branch of reality, a parallel universe where your actions have consequences, but which remains separate from your original timeline. This approach preserves causality within each branch, while allowing for the possibility of time travel and alternate histories. Another proposed resolution suggests the existence of self-consistent loops. In this scenario, any attempt to change the past would inevitably lead to the very events that caused you to travel back in time in the first place. Your actions in the past become an integral part of the timeline, creating a closed loop that maintains the consistency of history. This resolution implies a universe where free will may be an illusion, and our choices are predetermined by the inescapable logic of temporal consistency. Quantum mechanics offers yet another intriguing perspective on the grandfather paradox through the many worlds interpretation. This theory posits that every possible outcome of a quantum event occurs, each in its own separate universe. Applied to time travel, it suggests that your journey to the past would automatically transport you to a parallel universe where your actions wouldn't affect your original timeline. In this multiverse of possibilities, paradoxes dissolve into a sea of infinite realities. As we delve deeper into these potential resolutions, we begin to grasp the profound implications the grandfather paradox has for our understanding of reality itself. It challenges our most fundamental assumptions about cause and effect, forcing us to confront the possibility that our existence is far more precarious and interconnected than we ever imagined. The choices we make, the actions we take, may ripple across time in ways we can scarcely comprehend. As we unravel the threads of causality, we find ourselves entangled in a cosmic tapestry beyond our comprehension. The choices we make ripple across time, but what if those ripples could travel upstream? Recent experiments in quantum physics hint at a universe where causality is not the immutable law we once believed. Could the future influence the past? And if so, what becomes of our cherished notions of cause and effect? Consider the concept of retrocausality in quantum physics, a mind-bending idea that suggests an effect can precede its cause. This radical notion challenges our most fundamental understanding of how the universe operates. Imagine a world where every action is not just a consequence of the past, but potentially a harbinger of the future. In this reality, the arrow of time becomes less of a straight line and more of a Mobius strip, twisting and looping back upon itself in ways our minds struggle to grasp. The implications of retrocausality extend far beyond the realm of theoretical physics. They seep into the very foundations of our philosophical understanding of free will and determinism. If the future can influence the past, are our choices truly our own? Or are we merely actors in a cosmic play, our lines already written by events yet to come? The grandfather paradox, once a thought experiment confined to the realm of science fiction, now takes on new dimensions of complexity in light of these quantum revelations. As we grapple with these mind-bending concepts, we encounter the Novikov self-consistency principle, a theoretical framework that attempts to resolve causal paradoxes. This principle asserts that any actions taken by a time traveler must be consistent with the established timeline. In other words, the universe conspires to prevent contradictions, ensuring that any changes made to the past are already accounted for in the future from which the traveler came. But how can this be? How can the fabric of reality be so flexible yet so unyielding? To truly appreciate the depth of this conundrum, we must turn our attention to real-world experiments that seem to defy our understanding of cause and effect. Consider the whether Now picture a second measurement made after the first, capable of erasing the information gathered by the initial observation. In a universe governed by classical causality, this should have no effect on the particle's behavior, and yet the evidence suggests otherwise. It's as if the particle knows in advance that its information will be erased, adjusting its behavior accordingly. But how can a particle in the present respond to a future that hasn't yet occurred? This experimental evidence forces us to confront the possibility that our entire conception of reality might need to be revised. The comfortable linearity of time, the reassuring progression from cause to effect, begins to look less like an immutable law of nature and more like a convenient illusion, a simplification our minds use to make sense of a far more complex and interconnected universe. As we ponder these possibilities, we must ask ourselves, what if causality itself is merely an artifact of our limited perception? Perhaps like the Flatlanders in Edwin Abbott's Flatland, we are beings trapped in a lower dimensional understanding of a higher dimensional reality. Our perception of cause and effect might be nothing more than shadows on the wall of Plato's cave, crude approximations of a truth too vast and intricate for our minds to fully comprehend. The grandfather paradox, viewed through this new lens, becomes more than just a puzzling thought experiment. It becomes a key that unlocks the door to a new understanding of reality itself. It challenges us to expand our minds, to reach beyond the comfortable confines of linear thinking, and embrace a universe where past, present, and future are not fixed points, but fluid, interconnected states of being. In this new paradigm, time travel paradoxes are not problems to be solved, but windows into the true nature of existence. They reveal a universe far stranger and more wonderful than we ever imagined, where the boundaries between cause and effect are as permeable as the event horizon of a black hole, and where the very fabric of reality is woven from threads of possibility and paradox. As we gaze into the intricate tapestry of existence, a new paradigm emerges, one that challenges our fundamental understanding of reality itself. Imagine not just a single thread of time, but an infinite cosmic quilt, each patch a complete universe unto itself. This is the realm of the multiverse, a concept that stretches the boundaries of our imagination and might just hold the key to unraveling the knots of temporal paradoxes. The many worlds interpretation of quantum mechanics posits a reality far more expansive than we ever dreamed. In this view, every quantum event spawns new universes, each representing a different outcome. Consider the profound implications of this theory. Every decision you make, every path not taken, creates a new branch of reality. The universe where you chose coffee this morning coexists with the one where you opted for tea, separated by an invisible, impenetrable barrier. But how does this cosmic proliferation of realities interact with the concept of time travel? The multiverse theory offers a tantalizing solution to the paradoxes that have long plagued our temporal thought experiments. In this framework, a time traveler venturing into the past wouldn't alter their own timeline, but instead step into a parallel universe. The grandfather you might attempt to eliminate exists in a different reality from the one that gave birth to you. This interpretation transforms our understanding of causality and free will. If every possible outcome exists somewhere in the multiverse, what does it mean to make a choice? Are our decisions merely the act of selecting which universe we will experience next? The implications are staggering. In a multiverse where every possibility is realized, the concept of changing the past becomes meaningless. Instead, time travel becomes a form of universal navigation, a journey between already existing realities. Yet, this solution comes at a cost. Our intuitive understanding of reality, built on the comfortable foundation of a single, shared universe, crumbles in the face of infinite parallel worlds. The uniqueness of our experiences, the weight of our choices, all seem diminished when we consider that every alternative plays out somewhere in the cosmic ensemble. Consider the ethical quandaries that arise in a multiverse. If every decision creates new universes, are we responsible for the consequences of our actions across all realities? Imagine a world where every choice you make spawns countless new universes, each bearing the fruit of your decisions. The weight of such responsibility is almost unfathomable. Are we morally culpable for the suffering that might occur in universes created by our less noble choices? The multiverse theory also raises profound questions about personal identity. If there are infinite versions of you, each making slightly different choices, which one is the real you? Are we merely one expression of a vast, multidimensional self spread across countless realities? This concept challenges our very notion of individuality and forces us to reconsider what it means to be us. From a scientific perspective, the multiverse theory remains a topic of intense debate. While it offers elegant solutions to some of the most perplexing questions in quantum mechanics, it also raises new challenges. Critics argue that the theory lacks empirical evidence and may be fundamentally untestable. After all, how can we observe or measure universes that are, by definition, separate from our own? Yet, proponents of the many provides a coherent contemplate these mind-bending possibilities, we must also consider their implications for our understanding of time itself. In a multiverse, time might not be the linear progression we perceive, but a vast, multidimensional landscape. Our journey through this temporal terrain might be less like following a single path, and more like navigating a complex network of interconnected realities. The multiverse theory offers a resolution to time travel paradoxes by suggesting that they are, in fact, impossible. In this view, every potential outcome already exists in some reality. The act of time travel doesn't change the past, It simply relocates the traveler to a universe where the desired outcome has already occurred. This eliminates the logical contradictions that arise from altering one's own timeline. Just when you thought you had a grip on time travel, the cosmos throws another curveball. What if, instead of leaping between parallel universes, you could loop through your own timeline? Picture a roller coaster that brings you face to face with your past and future selves. Welcome to the mind-bending world of closed time-like curves. Closed time-like curves, or CTCs, are paths through space-time that loop back on themselves, allowing for the possibility of time travel to the past. Imagine tracing your finger along a circle drawn on paper. No matter where you start, you'll eventually return to the same point. Now, replace that circle with the fabric of space-time itself, and you've got a rudimentary understanding of a CTC. But why should we take these cosmic loops seriously? It turns out that CTCs aren't just the stuff of science fiction. They're supported by solutions to Einstein's field equations, the mathematical foundation of general relativity. Two famous examples stand out: the Gödel universe and the Tipler cylinder. Kurt Gödel, best known for his incompleteness theorems in mathematics, proposed a solution to Einstein's equations in 1949 that described a rotating universe. In this cosmic merry-go-round, the very structure of space-time twists and turns, creating paths that circle back through time. The Gödel universe serves as a theoretical playground where the arrows of time bend into loops, challenging our notion of a linear, forward-marching reality. Frank Tipler, on the other hand, envisioned a more concrete, albeit equally improbable, scenario. Picture an infinitely long cylinder, massive beyond comprehension, spinning at incredible speeds. Tipler's calculations suggested that such an object could warp space-time around it, forming CTCs in its vicinity. While we're unlikely to encounter planet-sized, rapidly rotating cylinders anytime soon, the Tipler cylinder illustrates how extreme gravitational conditions might give rise to these temporal loops. The existence of CTCs raises profound questions about causality, the relationship between cause and effect that forms the bedrock of our understanding of the universe. In a world with CTCs, events could influence their own past, creating potential paradoxes that make the grandfather paradox look like child's play. Imagine receiving a message from your future self, warning you about a mistake you're about to make. You heed the warning, avoiding the error. But in doing so, you've changed the future that led to the warning being sent in the first place. This is the kind of logical pretzel that CTCs can twist our minds into. But the implications of CTCs go far beyond mere logical conundrums. They strike at the heart of our conception of free will and determinism. If your future actions can influence your past, were your choices ever truly your own? Or are we all simply actors in a predetermined cosmic play? Are apparent decisions merely the unfolding of a script written in the very structure of space-time? Consider a scenario where you encounter your past self on a CTC. You share knowledge of future events, altering the course of your own history. But if your past is changed, how did you become the future self that returned to change it? This circularity of cause and effect challenges our linear understanding of time and raises questions about the nature of identity and consciousness. Some physicists have proposed resolutions to these paradoxes. Igor Novikov's self-consistency principle suggests that the universe simply won't allow contradictory events to occur along CTCs. In this view, any attempt to change the past would inevitably fail, or inadvertently cause the very events you were trying to prevent. It's as if the universe has a built-in safeguard against logical inconsistencies, ensuring that cause and effect remain intact, even if they form a closed loop. But what if CTCs are more than just theoretical constructs? Recent research into these temporal oddities has focused on their potential feasibility and the conditions under which they might exist. While we're far from building a time machine, the exploration of CTCs offers tantalizing insights into the nature of time and reality itself. For instance, some theories suggest that microscopic CTCs might exist at the quantum level, influencing the behavior of particles in ways we're only beginning to understand. If true, this could have profound implications for our understanding of quantum mechanics and the fundamental nature of reality. It might even provide a bridge between the seemingly incompatible worlds, of quantum physics and general relativity. As we contemplate the existence of CTCs, we're forced to confront the possibility that time is far more complex and malleable than we ever imagined. The comfortable linearity of past, present, and future may be an illusion, a simplification of a reality where all moments exist simultaneously, interconnected in a vast multi-dimensional tapestry of space-time. Picture your life as an intricate tapestry, each thread now philosophical debate surrounding free will and determinism has raged for centuries. The introduction of time travel paradoxes adds a new layer of complexity to this age-old question. As we stand at the crossroads of infinite possibilities, we must confront a startling possibility. Our actions may be part of a predetermined sequence of events, shaped by the inexorable march of time itself. Imagine for a moment that you could travel back in time and influence your own past. This seemingly innocuous act creates a causal loop, a circular chain of events where each point in time becomes both the cause and effect of every other point. In this scenario, your future self's actions have already shaped your past choices. Consider this: are you truly making decisions or simply acting out a predetermined script written by the universe itself? The implications of causal loops on personal agency are profound. If your future self influences your past actions, were those actions ever truly free? This paradoxical situation challenges our fundamental understanding of choice and free will. It suggests that our decisions may be part of a complex, interconnected web of events that extends both forward and backward in time. But the rabbit hole of free will in a paradoxical universe goes even deeper when we consider the many worlds interpretation of quantum mechanics. This theory posits that every quantum event spawns new universes, each representing a different outcome. In this vast multiverse, every possible choice you could make is realized in some parallel reality. At first glance, this might seem to support the existence of free will. After all, if every choice is made somewhere, doesn't that imply freedom of choice? However, this interpretation raises a perplexing question. If all possible choices are predetermined to occur across the multiverse, is any single decision truly free? Or are we simply playing out an infinite number of predetermined scripts, each one a slight variation on the others? The ethical implications of a deterministic universe are equally mind-bending. If our actions are predetermined by the structure of space-time or the branching of parallel universes, can we be held morally responsible for them? This question strikes at the heart of our justice systems, our social structures, and our very concept of personal responsibility. Imagine a courtroom where the defendant argues that their crime was inevitable, predetermined by the cosmic tapestry of time itself. How would we approach concepts like punishment or rehabilitation in a universe where free will is an illusion? These are not mere philosophical musings, but questions that could fundamentally reshape our understanding of ethics and morality. Recent advances in neuroscience have added yet another layer to this complex debate. Studies indicate that our decision-making processes are influenced by unconscious factors, suggesting that our sense of free will may be an illusion shaped by brain activity occurring prior to our conscious awareness. This research implies that our choices may be determined by neural processes beyond our control, further challenging the notion of free will. Yet, even as we grapple with these mind-bending concepts, we must consider a paradoxical possibility. Perhaps our sense of free will, illusory though it may be, is a necessary construct for navigating a reality filled with temporal paradoxes and quantum uncertainties. In a universe where causality can loop back on itself and where every possible outcome exists simultaneously, the illusion of choice may be the thread that holds our perception of reality together. The grandfather paradox serves as a powerful lens through which we can examine the tension between free will and determinism. It forces us to confront the possibility that our choices may be constrained by the very fabric of space-time, challenging our deepest assumptions about agency and responsibility. In a reality where time is not a linear progression, but a vast, multidimensional landscape, the concept of free will becomes as fluid and malleable as time itself. As we navigate the fluid landscape of time and free will, we encounter another paradox that challenges our very notion of truth itself. Imagine a statement so deceptively simple, yet so profoundly perplexing that it has confounded philosophers for millennia. What if a single sentence could unravel the fabric of logic? Consider this. This statement is false. In just 5 words, we find ourselves trapped in a labyrinth of circular reasoning. If we assume the statement is true, then it must accurately describe itself as false. However, if it is indeed false, then the statement is actually true. This mind-bending contradiction is the essence of the liar paradox, a classic puzzle that has puzzled thinkers since ancient times. The roots of this paradox stretch back to the Greek philosopher Epimenides, who famously declared all Cretans are liars. This self-referential statement creates a similar logical quandary. If Epimenides, himself a Cretan, speaks the truth, then he must be lying. But if he's lying, then his statement might be true. It's a dizzying dance of truth and falsehood that seems to defy resolution. In the realm of modern logic, the liar paradox takes on a more formalized structure. Logicians grapple with statements like, "This sentence is false," which encapsulate the essence of how self-reference can lead to logical contradictions. Such statements challenge our ability to classify assertions into simple categories of truth or falsehood. They force us to confront the limitations of traditional frameworks that rely on processes. As we delve deeper into this logical conundrum, we find that it's not merely an abstract puzzle for philosophers to ponder. The liar paradox has far-reaching implications that touch upon the nature of language, the limits of formal systems, and even the foundations of mathematics and computer science. One proposed solution to this paradox comes from the work of Alfred Tarski, who suggested a hierarchy of languages. In this framework, statements about truth must be made in a higher-level language to avoid self-reference. This approach helps to prevent contradictions by establishing a clear separation between different levels of truth claims. But while this solution offers a way to manage the paradox within formal systems, it doesn't entirely dispel the underlying mystery. Another intriguing approach is that of dialetheism, a philosophical stance that accepts that some statements can be both true and false simultaneously. This perspective challenges our classical binary view of truth and offers a way to handle self-referential paradoxes without resorting to contradictions. It's a radical departure from traditional logic, but one that might be necessary to fully grapple with the complexities of self-reference. The liar paradox shares a deep connection with one of the most profound results in 20th century mathematics, Gödel's incompleteness theorems. Kurt Gödel demonstrated that in any sufficiently complex formal system, there are statements that cannot be proven true or false within the system itself. This result echoes the self-referential issues posed by the liar paradox, highlighting fundamental limitations in our ability to create complete and consistent logical frameworks. Consider the implications of these ideas for artificial intelligence and computer science. As we strive to create machines that can reason and make decisions, we must carefully manage self-referential constructs to avoid paradoxical outcomes. Recursive functions in programming, for instance, must have proper termination conditions to prevent infinite loops, a practical manifestation of the logical circles we encounter in the liar paradox. The paradox serves as a humbling reminder of the complexity inherent in our attempts to formalize reasoning. It challenges us to question our most basic assumptions about truth and invites ongoing exploration of alternative frameworks for understanding the world. Perhaps the resolution to this ancient puzzle lies not in finding a definitive answer, but in embracing a more nuanced and flexible concept of truth itself. As we sail through the turbulent waters of philosophical inquiry, we encounter a paradox that threatens to capsize our very notion of identity. Picture an ancient vessel, its timbers creaking with the weight of centuries, each plank and rope bearing witness to countless voyages across treacherous seas. This is no ordinary ship, but the legendary vessel of Theseus, a paradox that has challenged philosophers for millennia. Imagine, if you will, that over the course of many years, every single component of this ship is gradually replaced. The worn planks are swapped for fresh timber, frayed ropes exchanged for new ones, and tattered sails unfurled anew. As the final original piece is removed, a profound question emerges. Is this still the same ship that Theseus once sailed? And if not, at what precise moment did it cease to be? This thought experiment, known as the Ship of Theseus paradox, strikes at the heart of our understanding of identity and persistence through time. It challenges us to question the very nature of what makes an object, or indeed a person, fundamentally itself. As we peel back the layers of this enigma, we find ourselves adrift in a sea of philosophical uncertainty. Consider the approach of mereological essentialism, which posits that an object's identity is inextricably tied to its physical components. Through this lens, the moment the first piece of Theseus's ship is replaced, it ceases to be the original vessel. But does this align with our intuitive understanding of identity? After all, we routinely replace parts of objects without considering them fundamentally altered. Perhaps a more nuanced perspective lies in the realm of four-dimensionalism. This view suggests that objects are not merely three-dimensional entities existing in the present, but rather four-dimensional beings extended through time. In this framework, the ship's identity persists as long as there is a continuity of form and function, even as its individual components change. The ship becomes a temporal worm stretching across the fourth dimension, maintaining its essence through the flow of time. But the implications of the Ship of Theseus extend far beyond mere objects. They ripple through the very core of our understanding of personal identity. Consider this: every cell in your body is replaced over time, yet you still consider yourself the same person. Are you in fact the same individual you were a decade ago, or have the gradual changes in your body and mind created an entirely new being? This question of personal identity raises profound implications for our understanding of consciousness, memory, and the nature of the self. If we are not the same person we were in the past, what does this mean for concepts of responsibility, guilt, or achievement? How can we reconcile our intuitive sense of continuous selfhood with the reality of constant physical and mental change? The paradox also casts a long shadow over legal and cultural concepts in the realm of historical. Modern variations of the Ship of Theseus paradox further complicate our understanding of identity. Consider the grandfather's axe thought experiment, where a family heirloom axe has had both its head and handle replaced over generations. Is it still the same axe that belonged to the grandfather? Or take the science fiction concept of teleportation, where an individual is disassembled at the molecular level and reassembled elsewhere. Is the person who emerges from the teleporter the same individual who entered it? As we grapple with these questions, we begin to suspect that the resolution to the Ship of Theseus paradox might require a fundamental shift in how we conceive of objects and identity. Perhaps identity is not an inherent property of objects at all, but rather a conceptual construct that we impose upon the world. This perspective suggests that identity may be more fluid and context-dependent than we typically assume, shaped by our perceptions, cultural norms, and pragmatic needs. The implications of this paradox extend far beyond philosophy, reaching into the realms of cognitive science and our understanding of consciousness. By questioning the nature of identity and change, we open new avenues for exploring the mechanisms of memory, the continuity of consciousness, and the very essence of what it means to be a persistent self in a world of constant flux. From the fluid nature of identity, we now step onto seemingly solid ground, only to find it crumbling beneath our feet. Consider this: before you can complete a single step, you must first cover half the distance, then half of the remaining half, and so on ad infinitum. How then can you ever reach your destination? This simple question unravels the very fabric of our understanding of motion and time, plunging us into the depths of Zeno's dichotomy paradox. Zeno of Elea, a pre-Socratic Greek philosopher, crafted a series of paradoxes designed to challenge our most fundamental assumptions about reality. His dichotomy paradox in particular presents us with a logical conundrum that seems to render even the simplest act of movement impossible. Imagine yourself poised to take a step forward. Before you can complete that step, you must first traverse half the distance. But before you can cover that half, you must cover a quarter of the original distance, and before that quarter, an eighth. As you mentally divide the distance into infinitely smaller fractions, you find yourself paralyzed by an endless sequence of prerequisite movements. The paradox forces us to confront a startling possibility. Could it be that our everyday experience of motion is fundamentally flawed? That the simple act of walking across a room requires us to complete an infinite number of tasks in a finite amount of time? This notion strikes at the heart of our intuitive grasp of reality, suggesting that if an infinite process is indeed required to complete a finite task, motion itself might be fundamentally impossible. Yet, we move, we walk, we run, we dance. The world around us is in constant flux. How can we reconcile this apparent contradiction? The tension between our lived experience and the logical implications of Zeno's paradox invites us to question the very nature of space, time, and infinity itself. Zeno's paradoxes were not mere philosophical curiosities. They were designed to demonstrate profound contradictions in the notion of motion and change, challenging the assumptions of his contemporaries about the fundamental nature of reality. These thought experiments serve as a gateway to deeper contemplation about the structure of the universe and our place within it. Consider, for instance, the paradox of Achilles and the tortoise. In this scenario, the fleet-footed Achilles gives a head start to a tortoise in a race. By the time Achilles reaches the tortoise's starting point, the tortoise will have moved forward. When Achilles reaches that new position, the tortoise will have advanced again. This process continues indefinitely, seemingly preventing Achilles from ever overtaking the slower tortoise. These paradoxes all stem from the problem of infinite divisibility. They challenge us to grapple with the concept of continuity in space and time. Are these fundamental aspects of our reality truly continuous, or might they be ultimately discrete at some microscopic scale? The influence of Zeno's paradoxes extends far beyond ancient Greek philosophy. They have played a crucial role in the development of mathematical concepts, particularly in the field of calculus. The tools of calculus provide a framework for understanding infinite processes and continuous motion, offering a resolution to the paradox by demonstrating that infinitely many steps can indeed result in a finite journey. Modern mathematics shows us that while there are infinitely many steps in Zeno's paradox, their size diminishes quickly enough to allow for the completion of a finite journey. This mathematical insight invites us to reconsider our intuitive understanding of infinity and its relationship to the finite world we inhabit. The relevance of Zeno's paradoxes extends into the realm of modern physics, where they continue to inform discussions about the nature of space-time in quantum mechanics. At the quantum scale, our classical notions of continuity break down, and we're forced to confront a reality that defies our macroscopic intuitions. Consider the Planck length, the smallest measurable distance. Philosophical inquiry. Zeno's dichotomy. Paradox serves as a reminder of the complexities involved in understanding motion and infinity. It encourages deeper philosophical reflection on the nature of existence and our place in the universe. As we grapple with these concepts, we're invited to question our most basic assumptions about reality and to embrace the wonder and mystery that lie at the heart of our existence. 10. Calculus. Taming infinity's wild frontier. As we ponder the mysteries of existence, our journey through paradox leads us to an unexpected destination, the realm of mathematics. Imagine a world where infinity becomes a tool, where the impossible becomes calculable. Welcome to the frontier of calculus, where the very paradoxes that once paralyzed our understanding of motion now propel us toward new horizons of knowledge. In the 17th century, mathematicians like Isaac Newton and Gottfried Wilhelm Leibniz embarked on a quest to unravel the enigmas of motion and change. Their journey was inspired in part by the ancient puzzles posed by Zeno of Elea. Where philosophers saw impasse, these pioneers of calculus saw opportunity. They crafted a mathematical framework that would not only address the challenges presented by Zeno's paradoxes, but would also revolutionize our understanding of the physical world. Consider the dichotomy paradox, a thought experiment that seems to render motion impossible through an infinite series of halvings. How can one ever complete a journey if there are always more divisions to traverse? Calculus offers a surprising answer by embracing infinity itself. Through the concept of limits, mathematicians found a way to sum infinite series, demonstrating how an endless number of steps can converge to a finite result. This elegant solution not only resolves the apparent contradiction in Zeno's paradox, but also opens up new avenues for describing continuous change. At the heart of calculus lie three fundamental concepts: limits, derivatives, and integrals. Each of these tools provides a unique lens through which to view the world of continuous change. Limits allow us to approach infinity without ever quite reaching it, much like Achilles forever closing the gap with the tortoise. Derivatives capture the essence of instantaneous change, revealing the rate at which quantities transform from one moment to the next. Integrals, on the other hand, enable us to accumulate these infinitesimal changes, building complex wholes from countless tiny parts. Imagine standing at the edge of a cliff, watching waves crash against the shore below. With calculus, we can describe the precise motion of each water droplet, from the crest of the wave to its final splash against the rocks. We can calculate the force of the impact, predict the erosion of the cliffside over time, and even model the intricate patterns of foam left behind on the sand. What once seemed like an impossibly complex system becomes a dance of equations, each variable intertwining with the others in a mathematical ballet. But as we wield the power of calculus to tame infinity, we must pause to consider the philosophical implications of our mathematical conquest. Have we truly resolved the paradoxes that inspired this field, or have we merely shifted them to a higher plane of abstraction? The use of infinity as a mathematical tool raises profound questions about the nature of reality and our ability to describe it. Consider the concept of continuity, so central to calculus. We model the physical world as a seamless fabric, infinitely divisible and smooth. Yet at the quantum scale, reality reveals itself to be granular and discrete. How do we reconcile these seemingly contradictory views? Perhaps the paradoxes of Zeno have not been vanquished but transformed, challenging us to probe even deeper into the foundations of mathematics and physics. Despite these philosophical quandaries, the practical power of calculus is undeniable. From the orbits of planets to the flow of electricity, from the spread of populations to the optimization of economic systems, calculus provides us with the tools to describe and predict the behavior of dynamic systems. Engineers use it to design bridges that can withstand the forces of nature, while physicists employ it to unravel the mysteries of the cosmos. In each application, we see the legacy of those ancient paradoxes, now transformed into engines of discovery. As we reflect on the journey from Zeno's puzzles to the development of calculus, we find a testament to human ingenuity and the power of abstract thought. The very challenges that once seemed to negate the possibility of motion have become the foundation for our most sophisticated understanding of change. Calculus has given us a language to describe the fluidity of the universe, allowing us to peer into the infinite and extract meaning from its depths. 11. The barber's razor. Logic turned against itself. From the fluid depths of calculus, we now turn to a razor-sharp edge of logic that threatens to cut through the very fabric of reason. Picture a quaint barbershop in a small town where a simple sign hangs in the window: "I shave all and only those who do not shave themselves." As you ponder this innocent-seeming rule, a troubling question begins to gnaw at the edges of your mind. Who shaves the barber? This seemingly innocuous scenario, introduced by the brilliant mind of Bertrand Russell in the early 20th century, serves as a classic illustration of a self-referential paradox that exposes fundamental issues in logic and set theory. As we unpack this puzzle, known as the barber possibility. But what makes this paradox so profoundly unsettling is not merely its logical impasse, it's the far-reaching implications it holds for the entire edifice of mathematics and reason. The barber paradox emerged during a time of great upheaval in the world of mathematics. Brilliant minds were striving to establish a solid foundation for their discipline, seeking to build a tower of knowledge that would reach the heavens of certainty. Yet, like the biblical Tower of Babel, their efforts were confounded by an unexpected complication: the problem of self-reference. Imagine you're constructing a vast library of knowledge, each book representing a set or a concept. As you organize these tomes, you realize that some books might need to reference themselves, or include descriptions of other books. But what happens when a book claims to catalog all books that don't catalog themselves? Should it include itself in its pages? This is the essence of Russell's paradox, of which the barber paradox is a more accessible illustration. The implications of this paradox extend far beyond the confines of a small-town barbershop. It forces us to reconsider the very rules and definitions we use to categorize and analyze sets, the fundamental building blocks of mathematics. How can we construct a consistent system of logic if self-reference leads to such irreconcilable contradictions? In response to this crisis, mathematicians and logicians began developing more robust frameworks to avoid these pitfalls. One significant approach was the development of type theory, which categorizes sets into different types to prevent self-reference. In this system, a set of a certain type cannot contain sets of the same or higher type, effectively avoiding the circular definitions that lead to paradoxes. But the ripples of the barber paradox spread even further, influencing philosophical inquiries into the nature of truth, self-reference, and the limits of human cognition. It serves as a cautionary tale about the dangers of assuming that all logically consistent statements can be assigned a truth value. Some statements, it seems, are neither true nor false, but exist in a liminal space that challenges our binary notions of logic. As we grapple with these ideas, consider how they might apply to your own thought processes. Have you ever caught yourself in a circular argument, unable to break free from a loop of reasoning? The barber paradox reminds us that even our most carefully constructed logical systems can harbor hidden contradictions, waiting to be exposed by the right line of questioning. In the realm of computer science, the legacy of the Barber paradox lives on. Programmers must be ever vigilant against self-referential constructs that can lead to infinite loops or logical inconsistencies. Database designers must carefully structure their systems to avoid paradoxical relationships between datasets. The ghost of the paradoxical barber haunts the silicon halls of our most advanced technologies, a constant reminder of the need for rigorous logical frameworks. Yet even as we develop more sophisticated tools to navigate these logical labyrinths, new approaches emerge that challenge our traditional notions of consistency. Paraconsistent logic, for instance, allows for contradictions to coexist without leading to logical explosion. In this framework, the barber's dilemma might be seen not as an irresolvable paradox, but as a complex truth that transcends simple binary logic. 12. The paradox of choice, when more becomes less. As we step away from the logical labyrinths of paraconsistent reasoning, we find ourselves in a world where abundance breeds anxiety. Imagine a realm where having more options actually makes you less satisfied. How could the freedom to choose become a burden rather than a blessing? This is the essence of the paradox of choice, a concept that challenges our fundamental assumptions about decision-making and happiness. Consider the simple act of selecting a jar of jam at the supermarket. You approach the shelf, expecting to make a quick decision, only to find yourself confronted with an overwhelming array of flavors, brands, and sizes. As you stand there, paralyzed by indecision, you're experiencing firsthand the cognitive overload that lies at the heart of this paradox. Researchers have found that when presented with a larger assortment of jams, consumers are actually less likely to make a purchase. The increased variety leads to more deliberation and second-guessing, ultimately resulting in lower satisfaction with the final choice. But why does this happen? Our minds, evolved to navigate a world of scarcity, find themselves ill-equipped to handle the superabundance of modern life. Each decision we make requires mental energy, and as we face an ever-increasing number of choices throughout our day, we experience what psychologists call decision fatigue. This cognitive exhaustion diminishes our ability to make satisfying choices, leaving us feeling drained and unsure. Moreover, the specter of regret looms large in the face of numerous options. When we choose one item from among many, we're simultaneously not choosing all the others. This creates a nagging sense that we might have made the wrong decision, that another option could have been better. The joy of our selection becomes overshadowed by the fear of missed opportunities, a psychological burden that grows heavier with each additional choice we face. Think about the last time you scrolled through a streaming service, searching for the perfect movie to watch. As you browse through hundreds of titles, each one promising entertainment, you might find yourself spending more time choosing than actually watching. This is the paradox of choice in action, transforming what should be a pleasurable experience into a source of stress and indecision. The expectation of chosen a good enough option from a smaller selection. Psychologists have identified two distinct approaches to decision-making: maximizing and satisficing. Maximizers strive to make the best possible choice by exploring all available options. While this might seem like a prudent approach, it often leads to increased anxiety and regret. Satisficers, on the other hand, are content with a choice that meets their criteria, even if it's not necessarily the absolute best. This more relaxed approach to decision-making often results in greater satisfaction and less stress. The implications of the paradox of choice extend far beyond consumer behavior. Consider the realm of romantic relationships in the age of dating apps. With a seemingly endless array of potential partners at our fingertips, we might find ourselves constantly second-guessing our choices, always wondering if there's someone better just to swipe away. This abundance of options can lead to decreased satisfaction with relationships, as the grass always seems greener on the other side of the dating profile. In the professional world, The paradox of choice manifests in the overwhelming number of career paths available to modern workers. While having options is generally positive, the pressure to choose the right career can be paralyzing, leading to indecision and dissatisfaction. The fear of making the wrong choice can prevent individuals from fully committing to any path, resulting in a sense of stagnation and unfulfillment. So how do we navigate this paradox? How can we enjoy the benefits of choice without succumbing to its pitfalls? One approach is to practice decision simplification. By consciously limiting our options or establishing clear criteria for our choices, we can reduce the cognitive load of decision-making. This might mean creating a capsule wardrobe with fewer clothing items, or setting specific parameters for our job search. Another strategy is to adopt a satisficing mindset. Instead of striving for the perfect choice, we can learn to appreciate good enough decisions. This doesn't mean settling for mediocrity, but rather recognizing that the pursuit of perfection often comes at the cost of satisfaction and peace of mind. Practicing gratitude and acceptance can also help mitigate the negative effects of choice overload. By focusing on the positive aspects of our decisions and accepting that no choice is perfect, we can reduce feelings of regret and enhance our overall satisfaction. This mindset shift allows us to appreciate the abundance of options as a privilege rather than a burden. 13. The bootstrap paradox. Information's Ouroboros. As we ponder the abundance of choices in our lives, let's consider a universe where even the concept of origin becomes uncertain. Picture receiving a gift from your future self, a gift that inspired your entire life's work. But if you created it because you received it, who really invented it? This mind-bending scenario introduces us to the bootstrap paradox, a concept that threatens to unravel our understanding of cause and effect. The bootstrap paradox, also known as the causal loop or ontological paradox, challenges our perception of time and causality. It emerges in scenarios where an object or piece of information travels back in time, only to become the catalyst for its own existence. Imagine a time traveler who journeys to the past, carrying a copy of a renowned novel. They present this book to a young, aspiring writer who, inspired by its brilliance, goes on to pen the very same work. The question arises, where did the story truly originate? This paradox creates a self-sustaining loop with no clear point of origin, a literary Ouroboros devouring its own tale. The book exists because it was written, but it was written because it already existed. This circular logic defies our traditional understanding of cause and effect, where we expect every effect to have a preceding cause. Consider the implications of such a paradox on our concept of creativity and innovation. In a universe where time travel is possible, can we ever be certain of the true origin of an idea? The bootstrap paradox suggests a reality where information and objects can exist in a state of perpetual creation and recreation, challenging our notions of authorship and originality. The paradox extends beyond the realm of literature and art. Imagine a scientist who receives advanced technological blueprints from the future. These blueprints enable them to create the very time machine that will eventually be used to send the plans back. The technology exists because it was invented, but it was invented because it already existed. This cyclic causality creates a closed time-like curve, a path through space-time that loops back on itself. In the context of physics, the bootstrap paradox intersects with theories of closed time-like curves and the possibility of sending information backwards through time. These concepts, while theoretically possible within the framework of Einstein's general relativity, raise profound questions about the nature of time itself. If information can loop back on itself, does time flow in a single direction, or is it more akin to a vast interconnected web? The paradox also challenges our understanding of free will and determinism. In a universe where events can be their own cause, how much agency do we truly possess? Are our actions predetermined by information from the future, or do we have the power to break these causal loops? Proposed resolutions to the bootstrap paradox offer intriguing possibilities. The concept of multiple timelines suggests that each instance of time travel creates a new branch of reality. preventing true paradoxes from occurring. This principle suggests that paradoxes are impossible because the universe naturally prevents contradictory events from occurring. In the case of our novel, the principle would argue that the book was always meant to be delivered by the time traveler, creating a stable, if circular, chain of events. These resolutions, however, raise their own philosophical quandaries. If multiple timelines exist, what determines which reality we experience? And if the universe enforces self-consistency, does this imply a form of cosmic determinism? The bootstrap paradox invites us to reconsider our fundamental assumptions about reality. It suggests a universe where the concepts of before and after may be more fluid than we imagine, where information and objects can exist in a state of perpetual creation and recreation. This paradox challenges us to expand our thinking beyond linear causality and consider a reality where effect and cause dance in an eternal, impossible embrace. 14. The Sorites paradox when categories crumble. From the fluidity of time, we now turn our gaze to the boundaries of meaning itself. Picture a world where even the simplest concepts, a heap of sand, a bald head, or a tall person, become elusive, slipping through our fingers like grains of sand. What happens when our categories crumble and the very foundations of language begin to dissolve? The Sorites paradox, also known as the paradox of the heap, presents a profound challenge to our understanding of categories and definitions. It exposes the inherent vagueness in many of our everyday concepts, revealing the difficulty of drawing precise boundaries in a world of continuous spectra. Imagine a heap of sand before you. Now, remove a single grain. Is it still a heap? You remove another and another. At what precise point does it cease to be a heap? This seemingly innocuous question unravels the very nature of categorization. Attributed to the ancient Greek philosopher Eubulides of Miletus, the Sorites paradox extends far beyond mere piles of sand. Consider the concept of baldness. How many hairs must a person lose before they're considered bald? Or ponder the notion of tallness. At what exact height does someone transition from being of average stature to tall? These questions may seem trivial, but they harbor a paradox so profound it threatens to destabilize the scaffolding of human knowledge and decision-making. The heart of the Sorites paradox lies in the concept of vagueness. Our language is filled with terms that lack precise boundaries. Tall, rich, old, yet we use them confidently in everyday discourse. The paradox exposes the limitations of traditional logic, which typically operates on the assumption that categories are clearly defined and that every statement can be classified as either true or false. But in a world of continuous spectra, how can we maintain such rigid distinctions? Philosophers have grappled with this conundrum for centuries, proposing various approaches to resolve the paradox. One such approach is epistemicism, which posits that there is indeed a precise cutoff point between a heap and a non-heap, but this point is unknowable to us. This view preserves the law of excluded middle, suggesting that every statement is either true or false, while attributing vagueness to our lack of knowledge about the exact conditions that define the concept. Another intriguing resolution comes in the form of fuzzy logic. This approach rejects the binary nature of traditional logic, introducing degrees of truth. Instead of asking whether a collection of sand grains is or is not a heap, fuzzy logic allows us to assess the degree to which it is a heap. This nuanced perspective aligns more closely with our intuitive understanding of vague concepts, acknowledging that reality often exists in shades of grey rather than black and white. Supervaluationism offers yet another perspective. This theory suggests that while vague terms may not have precise boundaries, we can still reason about them consistently by considering all possible ways of making them precise, known as precisifications. A statement is considered true if it holds true under every precisification. false if it's false under every precisification, and otherwise indeterminate. This approach allows us to maintain logical consistency while acknowledging the inherent vagueness of certain concepts. The implications of the Sorite's paradox extend far beyond philosophical discourse, touching various aspects of our lives and society. In legal contexts, for instance, vague terms like reasonable or negligent can lead to borderline cases where it's unclear how the law should be applied. Small incremental changes in circumstances can lead to vastly different legal interpretations, with potentially life-altering consequences. In medicine, the paradox emerges in end-of-life care decisions, where terms like quality of life or terminal are often used. These concepts lack precise definitions, and small changes in a patient's condition might not clearly indicate a shift from one category to another. How do we make ethical decisions in such ambiguous territories? Even in the realm of artificial intelligence, the Sorite's paradox poses significant challenges. AI systems often rely on binary classifications, but the paradox suggests that these systems may struggle with concepts that do not have clear boundaries. How can we design algorithms that can navigate the nuanced, fuzzy boundaries of human language and decision-making? As we grapple with the Sorite's paradox, we're forced to confront the limitations of our categorical thinking. It challenges us to embrace a more nuanced understanding of reality, one that acknowledges the continuous nature of many phenomena. Perhaps the resolution lies knowledge and flux. As we step from the shifting standards of categorization, we encounter a new realm that even our most rational deductions can lead us astray. Picture a classroom where knowledge becomes a double-edged sword. The more the students know, the less they can predict. This is the essence of the unexpected examination paradox, a logical conundrum that challenges our understanding of knowledge, prediction, and the very nature of surprise. Imagine a teacher announcing to her class, "Next week you will have a surprise examination on one of the 5 weekdays." At first glance, this seems like a straightforward statement, but as the students, being clever logicians, begin to reason through the implications, they find themselves trapped in a web of contradictions. Their logical journey begins at the end of the week. They argue that the exam cannot occur on Friday, for if it hadn't happened by Thursday evening, it would no longer be a surprise. This elimination process continues backward through the week. Thursday is ruled out because, if Friday is impossible, it would be the last possible day, and thus not a surprise. The same reasoning eliminates Wednesday, Tuesday, and finally Monday. The students, following their impeccable logic, conclude that no examination is possible at all. Yet, when Wednesday arrives and the teacher distributes the exam papers, the students find themselves genuinely surprised. How can this be? Their reasoning seemed flawless, their logic impeccable, and yet reality has defied their carefully constructed argument. This paradox illuminates the complex interplay between knowledge, belief, and time. It forces us to confront the limitations of our logical frameworks when applied to scenarios involving both predictability and uncertainty. The student's reasoning, while seemingly valid at each step, leads to a conclusion that contradicts reality. This contradiction challenges our assumptions about what it means to know something will or won't happen. Consider how this paradox might play out in real-world scenarios. In financial markets, investors constantly attempt to predict future trends based on available information. Yet, market-moving events often catch even the most astute analysts by surprise. Similarly, in military strategy, the element of surprise remains a powerful tactic, despite extensive intelligence gathering and scenario planning. The unexpected examination paradox suggests that perfect prediction may be inherently impossible, even with seemingly complete information. But why does this paradox continue to perplex logicians and philosophers? Its persistence lies in its ability to expose the fragile nature of our epistemic certainty. It challenges us to reconsider what we mean when we claim to know something about the future. The paradox suggests that our knowledge is always in flux, subject to revision as new information becomes available or as time passes. Attempts to resolve this paradox have led to fascinating explorations in temporal and epistemic logic. Some philosophers argue that the paradox arises from a misunderstanding of the nature of knowledge and belief. They suggest that the student's error lies in assuming that their knowledge remains constant throughout the week. In reality, their knowledge state changes each day as the exam fails to materialize, altering the probabilities and their ability to predict. Others propose that the paradox reveals a fundamental limitation in our ability to reason about self-referential statements. The teacher's announcement creates a circular dependency between the student's knowledge and the occurrence of the exam. This circularity, they argue, makes it impossible to assign a definitive truth value to the statement, much like the famous liar's paradox. The unexpected examination paradox also intersects with deeper philosophical questions about free will and determinism. In a purely deterministic universe, could true surprises exist? If every event is the inevitable result of prior causes, how can anything be unexpected? Yet our subjective experience is filled with surprises and unforeseen events. This paradox invites us to contemplate the nature of surprise itself and its relationship to our limited knowledge and perception. Perhaps the resolution to this paradox lies not in finding a logical flaw or redefining our terms, but in embracing a more nuanced understanding of knowledge and prediction. It challenges us to recognize the dynamic nature of our beliefs and the inherent uncertainty in our predictions about the future. The paradox suggests that true knowledge often involves acknowledging the limits of what we can know with certainty. 16. The perfect crime, when flawlessness falters. As we step away from the shifting sands of prediction and uncertainty, we find ourselves confronting a paradox that challenges our very notions of perfection and criminality. Imagine a crime so flawlessly executed that it leaves not a single trace of evidence, not a whisper of suspicion, not even the faintest ripple in the fabric of reality. This is the concept of the perfect crime, a notion that has captivated the minds of philosophers, legal scholars, and storytellers for generations. But as we unravel this idea, we encounter a web of contradictions that force us to question the very nature of crime itself. Consider the fundamental paradox at the heart of this concept. If a crime is truly perfect, leaving absolutely no evidence of its occurrence, can we even call it a crime at all? In the realm of law and justice, the absence of evidence often equates to the absence of a crime. Yet, the idea of a perfect crime assumes a level of control and execution that may be unattainable in practice. It's a concept that exists in a liminal space between reality and imagination, challenging our understanding. The concept of a perfect crime emphasizes the sheer complexity of achieving absolute flawlessness in any endeavor, let alone one shrouded in secrecy and moral ambiguity. As we delve deeper into this paradox, we must confront the philosophical implications of perfection itself. Is perfection an attainable goal, or is it an ideal that forever eludes our grasp? In the context of crime, this question takes on a darker hue. The pursuit of the perfect crime becomes a twisted mirror of humanity's eternal quest for excellence, revealing uncomfortable truths about our capacity for both innovation and destruction. Real-world examples serve to illustrate the elusive nature of the perfect crime. History is replete with cases that were initially deemed unsolvable, only to be cracked open years or even decades later by advancements in forensic technology. What was once considered the epitome of criminal perfection crumbles in the face of scientific progress. These cases remind us that our definition of perfect is inherently tied to the limitations of our current knowledge and capabilities. The march of technology plays a crucial role in this ongoing dance between criminal ingenuity and investigative prowess. As forensic techniques become more sophisticated, the bar for what constitutes a perfect crime rises ever higher. DNA analysis, digital forensics, and other cutting-edge technologies have transformed the landscape of criminal investigation. Even the most seemingly insignificant traces, a stray hair, a partial fingerprint, a fleeting digital footprint, can now unravel the most carefully constructed criminal schemes. Yet, as we contemplate the technological arms race between criminals and investigators, we must also grapple with the ethical dimensions of the perfect crime. The very pursuit of such an ideal raises profound questions about human nature and morality. What drives individuals to seek perfection in acts of wrongdoing? Is it a desire for intellectual challenge, a misguided quest for superiority, or something darker still? The concept of the perfect crime serves as a mirror, reflecting our societal values and the boundaries we place on human behavior. Moreover, the idea of a perfect crime challenges our understanding of justice itself. If a crime could truly be committed without leaving any trace or causing any detectable harm, would it still be considered a violation of ethical or legal norms? This thought experiment pushes us to examine the foundations of our justice system and the principles upon which it is built. It forces us to confront the possibility that our notions of crime and punishment may be more complex and nuanced than we often assume. As we navigate this labyrinth of paradoxes, we begin to see that the concept of the perfect crime is not merely a theoretical exercise, but a lens through which we can examine broader questions about knowledge, certainty, and the limits of human achievement. It challenges us to reconsider our assumptions about the nature of evidence, the role of technology in society, and the very essence of criminal behavior. 17. The grandfather paradox revisited, reality's recursive riddle. As we return to the grandfather paradox, our journey through the labyrinth of temporal conundrums has transformed our perspective. The gun in your hand, once a simple tool of destruction, now symbolizes the intricate web of causality that binds the fabric of reality. The paradox before us is no longer just a thought experiment, but a gateway to understanding the very nature of existence itself. Consider how our exploration of closed time-like curves and bootstrap paradoxes has reshaped our view of time. The linear progression we once took for granted now appears as a complex tapestry, with threads of cause and effect intertwining in ways that challenge our most fundamental assumptions. The act of traveling back in time to confront your grandfather becomes not just a physical journey, but a traversal through the multidimensional landscape of possibility. In this new light, the paradox takes on a recursive quality. Each potential action or inaction creates a ripple effect through time, forming a self-referential loop that defies conventional logic. The question is no longer simply whether you can or cannot change the past, but how the very attempt to do so might be intricately woven into the causal structure of reality. Emerging theories in physics offer tantalizing new perspectives on this age-old puzzle. Post-selected quantum mechanics, for instance, suggests a universe where future events can influence the past, creating a framework where paradoxes might resolve themselves through complex quantum interactions. Imagine a reality where your decision to travel back in time is not just a choice made in the present, but an event that reverberates both forward and backward through time, shaping the very circumstances that led to your decision. The consistent histories approach provides another intriguing angle. It posits that our universe follows only those histories that are internally consistent, potentially eliminating paradoxical timelines from the realm of possibility. In this view, the act of attempting to change the past might itself be part of the consistent history that led to your existence. The gun in your hand becomes both the potential instrument of your grandfather's demise and the very reason for your birth, a cosmic Ouroboros of causality. These theories force us to grapple with profound philosophical questions. If our actions in the past are constrained by the need for creating an infinite branching structure of reality. In this framework, the paradox dissolves into a sea of possibilities. You may succeed in altering your timeline in one branch, while in another, your attempt fails, preserving the original sequence of events. But what does this mean for the concept of personal identity and responsibility? Are you still you if your actions spawn countless alternate versions of yourself? The exploration of these ideas extends far beyond the realm of theoretical physics. Real-world research into the nature of time and causality draws inspiration from these paradoxes. Scientists studying quantum entanglement and retrocausality are probing the boundaries of our understanding, seeking clues to the fundamental structure of reality. The grandfather paradox serves as a conceptual North Star, guiding inquiries into the nature of time itself. As we delve deeper into these mysteries, a profound realization emerges. The resolution to the grandfather paradox may require nothing less than a complete paradigm shift in our understanding of physics and philosophy. Our conventional notions of cause and effect, of past and future, of choice and consequence, may be woefully inadequate to describe the true nature of reality. 18. Conclusion. As we emerge from this labyrinth of paradoxes, our minds have been stretched and reshaped, forever altered by the intricate dance of logic and impossibility. The boundaries we once held as immutable have blurred, revealing a reality far more complex and wondrous than we dared imagine. These paradoxes are not mere intellectual puzzles to be solved and discarded, but gateways to profound understanding, challenging us to question the very foundations of our knowledge. Consider the words of Albert Einstein. The most beautiful experience we can have is the mysterious. It is the fundamental emotion which stands at the cradle of true art and true science. In grappling with these paradoxes, we have embraced that mystery, pushing the limits of human comprehension. Our journey through quantum mechanics, the nature of time, and the fabric of existence itself has led us to the precipice of new discoveries. As you drift into the realm between wakefulness and dreams, let these paradoxes swirl in your consciousness. In this liminal space, where the rigid structures of logic bend and time loses its linear march, you might glimpse something profound about the nature of reality. For it is in these moments of cognitive flexibility that we often find our greatest insights, our minds free to explore the vast possibilities the paradoxes reveal. Did you know that if you could somehow survive inside a black hole, you might see the entire future of the universe unfold before your eyes in a matter of moments? This mind-bending consequence of Einstein's theory of relativity is just one of the many fascinating concepts we'll explore in our journey through physics. As we delve into the fundamental laws that govern our universe, from the cosmic scale of galaxies to the subatomic realm of quantum particles, you'll discover that reality is far more incredible than any science fiction. Are you prepared to confront the profound implications of these ideas, even as they lull you into a contemplative state, perfect for drifting off to sleep? Picture yourself adrift in the infinite expanse of space, a lone explorer suspended in the cosmic void. As you float, seemingly motionless, you notice something peculiar. Despite the absence of any visible force acting upon you, your journey continues unabated. This observation challenges our intuitive understanding of motion and rest, beckoning us to explore one of the most fundamental principles in physics, Newton's first law of motion. At its core, Newton's first law introduces us to the concept of inertia, a property inherent to all matter in the universe. Inertia, in essence, is the resistance of any physical object to changes in its state of motion. This principle suggests that an object at rest tends to stay at rest, and an object in motion tends to stay in motion, unless acted upon by an external force. But what does this mean for our understanding of the cosmos and our place within it? Consider the frustration you might feel when attempting to halt a massive boulder rolling down a hill. The boulder's reluctance to change its motion is a direct manifestation of inertia. Conversely, imagine the graceful glide of a puck across an air hockey table, its smooth trajectory maintained by the near absence of friction. These everyday experiences offer glimpses into the profound nature of inertia and its role in shaping the physical world around us. The implications of inertia extend far beyond our terrestrial experiences. In the grand theatre of the cosmos, inertia plays a starring role in choreographing the celestial dance of planets, moons, and comets. The Earth's orbit around the Sun, for instance, is a testament to the enduring influence of inertia. Our planet, once set in motion, continues its elliptical path year after year, century after century, maintained by the delicate balance between its inertial motion and the gravitational pull of the Sun. But what does this reveal about the nature of change and stability in our universe? The concept of inertia challenges our perception of rest as the natural state of things. In a universe governed by Newton's first law, motion is the default state, and rest is merely a special case where the sum of all forces acting on an object is zero. This insight invites us to reconsider our understanding of change and permanence in the cosmos. Imagine a universe where objects, once set in motion, continue their journey indefinitely. In such a closely related to inertia, further illuminates the clockwork nature of the universe. This law states that the total momentum of a closed system remains constant over time. In the absence of external forces, the momentum of interacting objects is redistributed, but never created or destroyed. This conservation principle underpins the predictability of mechanical systems, from the collision of billiard balls to the gravitational interactions of celestial bodies. As we contemplate the implications of inertia and the conservation of momentum, we begin to perceive the universe as a vast, intricately connected mechanism. Each object, from the tiniest particle to the most massive galaxy, plays its part in this cosmic clockwork. The orbits of planets, the trajectories of comets, and even the motion of stars within galaxies all adhere to these fundamental principles, creating a symphony of motion that unfolds across the eons. However, as we stand in awe of the elegant simplicity of Newton's laws, we must also acknowledge their limitations. In the extreme conditions of the universe, near the event horizons of black holes, or in the realm of subatomic particles, the clockwork precision of Newtonian physics begins to falter. These frontiers hint at deeper, more exotic principles that govern reality at its most fundamental level. As we stand at the threshold of Einstein's revolutionary ideas, we find ourselves peering into a universe where time itself becomes as malleable as clay in the hands of a cosmic sculptor. Imagine two identical clocks, precision crafted to measure the passage of moments with unwavering accuracy. One remains firmly rooted on Earth, while its twin embarks on a cosmic odyssey, accelerating to velocities that approach the very speed of light. When these chronometric siblings are finally reunited, which will have aged more? This seemingly paradoxical question serves as our gateway into the realm of special relativity, where our most fundamental assumptions about reality are challenged and reshaped. Einstein's theory of special relativity, formulated in 1905, shattered the Newtonian concept of time as an absolute, unchanging dimension. In its place, we find a universe where time stretches and contracts like an elastic band, its rhythm intimately tied to the motion of the observer. This elasticity of time, known as time dilation, reveals itself most dramatically when objects or observers move at velocities approaching the cosmic speed limit, the speed of light. Consider the famous twin paradox, a thought experiment that illustrates the mind-bending consequences of time dilation. Two identical twins, let's call them Alice and Bob, begin their lives on Earth. Alice remains on our planet, while Bob embarks on a journey through the cosmos at nearly the speed of light. As Bob's spacecraft hurtles through space, time for him begins to slow down relative to his Earthbound sister. When Bob finally returns from his interstellar voyage, he finds that Alice has aged significantly more than he has. This scenario, once confined to the realm of science fiction, is now a mathematically proven consequence of Einstein's theories. But how can we reconcile this cosmic choreography of time with our everyday experiences? The key lies in understanding that time dilation effects become noticeable only at extreme velocities or in the presence of intense gravitational fields. In our daily lives, moving at speeds far below that of light, these effects are imperceptibly small. However, as we push the boundaries of technology and exploration, the elastic nature of time becomes increasingly relevant. Consider the Global Positioning System, GPS, a technology we often take for granted in our smartphones and navigation devices. The satellites that form the backbone of this system orbit Earth at speeds of about 14,000 kilometers per hour. At these velocities, the clocks aboard the satellites tick slightly faster than those on the ground due to time dilation. Additionally, the weaker gravitational field experienced by the satellites in orbit further affects the flow of time. Engineers must account for these relativistic effects to ensure accurate positioning, correcting for time differences that, while small, would quickly accumulate to create significant errors in location data. The implications of time dilation extend far beyond our current technological applications, potentially reshaping our approach to space exploration. Imagine a future where interstellar travel becomes a reality. As spacecraft approach the speed of light, time dilation could theoretically allow astronauts to traverse vast cosmic distances within their lifetime. While centuries might pass on Earth, the crew of such a vessel would experience the journey as lasting only a few years. This concept, known as time contraction, opens up tantalizing possibilities for exploring the far reaches of our galaxy, albeit with the bittersweet knowledge that the world left behind would have aged far more than the travelers. As we contemplate these cosmic implications, it's fascinating to consider how Einstein's revelations about the nature of time might relate to our personal experiences. Have you ever noticed how time seems to slow to a crawl when you're bored, yet flies by in moments of excitement or engagement? While these perceptual shifts aren't directly related to relativistic effects, they hint at the subjective nature of time in our consciousness. Our internal experience of time's passage is influenced by our mental state, much as the physical flow of time is affected by motion and gravity in Einstein's universe. The elastic nature of time revealed by special relativity is just the beginning of as we falling into a black hole might witness the entire future history of the universe unfold before their eyes in a matter of moments. 4. The quantum tango, particles in superposition. As we descend from the cosmic ballet of warped space-time near black holes, we enter a realm where reality itself becomes a shimmering mirage. Imagine a world where objects refuse to be pinned down, existing in a state of perpetual possibility until observed. Welcome to the quantum tango, where particles dance to the tune of probability, and our very act of looking shapes the nature of what we see. Consider a subatomic particle. Is it a wave or a particle? The answer might surprise you. It's both and neither until we look at it. This peculiar phenomenon, known as wave-particle duality, lies at the heart of quantum mechanics. It challenges our classical understanding of objects having definite properties, inviting us to reconsider the very fabric of reality. To grasp this concept, let's explore the famous double-slit experiment. Imagine firing particles, such as electrons or photons, at a barrier with two narrow slits. Classical physics would predict that these particles would create two distinct bands on a screen behind the barrier. However, the actual result is far more intriguing. When both slits are open, an interference pattern emerges. A series of alternating light and dark bands typical of waves. But here's where it gets truly bizarre. Even when we fire single particles through the apparatus one at a time, the interference pattern still emerges over time. It's as if each particle passes through both slits simultaneously, interfering with itself. This seemingly impossible behavior reveals the true nature of quantum entities. They exist in a superposition of states until measured. The implications of this experiment are profound. It suggests that at the quantum level, particles don't have definite positions or trajectories until they're observed. Instead, they exist as clouds of probabilities, their properties undetermined until the moment of measurement. This concept of superposition lies at the core of quantum mechanics, challenging our intuitive understanding of reality. But why does measurement seem to collapse this superposition into a definite state? This question has puzzled physicists and philosophers alike for nearly a century. Some interpret it as the observer playing a crucial role in shaping reality, while others propose that each measurement creates a branching of universes where all possible outcomes occur in separate, coexisting realities. As we grapple with these mind-bending concepts, we must also confront the uncertainty principle, formulated by Werner Heisenberg. This principle states that we cannot simultaneously know a particle's exact position and momentum with absolute accuracy. The more precisely we measure one property, the less certain we become about the other. This fundamental limitation isn't due to the inadequacy of our instruments, but rather an intrinsic feature of reality itself. The uncertainty principle underscores the probabilistic nature of quantum mechanics. It suggests that the universe, at its most fundamental level, is not deterministic. Instead, it's a realm of potentialities, where certainty exists only at the moment of observation. This realization has profound philosophical implications, challenging our notions of causality and free will. Consider how this quantum uncertainty might relate to our own cognitive processes. Could the unpredictability of our thoughts and decisions be a macroscopic manifestation of quantum indeterminacy? Some theorists propose that the human brain, with its intricate network of neurons, might leverage quantum effects to generate consciousness and creativity. While this remains a speculative idea, it invites us to ponder the connection between the quantum world and our subjective experience of reality. The concept of superposition isn't merely an abstract curiosity, it's finding practical applications in cutting-edge technology. Quantum computing harnesses this phenomenon, using quantum bits or qubits that can represent both 0 and 1 simultaneously. This allows quantum computers to perform complex calculations much faster than classical computers, potentially revolutionizing fields from cryptography to drug discovery. As we contemplate these strange quantum behaviors, we begin to sense that we've only scratched the surface of nature's mysteries. The dance of particles in superposition hints at an even more perplexing phenomenon: quantum entanglement. This spooky action at a distance, as Einstein famously called it, suggests that particles can be instantaneously connected across vast distances, challenging our understanding of space and time. 5. Spooky action at a distance, quantum entanglement. As we venture deeper into the quantum labyrinth, we encounter a phenomenon so profound it challenges the very fabric of our reality. Imagine two particles, separated by vast cosmic distances, yet intimately connected in ways that defy our classical understanding of the universe. This is the realm of quantum entanglement, where the boundaries of space and time blur, and the laws of physics as we know them seem to break down. Consider for a moment the implications of two particles instantaneously influencing each other across the cosmos. How can information travel faster than light, the universal speed limit? This apparent violation of causality sent shockwaves through the scientific community, leading Albert Einstein to famously describe quantum entanglement as so too has our ability to observe particles. Recent experiments have pushed the boundaries of what we once thought possible. Picture a satellite orbiting high above the Earth, beaming entangled photons to ground. Stations separated by vast distances. This is not science fiction, but a reality demonstrated by Chinese scientists in 2020. Their groundbreaking work showed that quantum entanglement could be maintained over incredible distances, challenging our notions of space and interconnectedness. The implications of these findings extend far beyond the realm of theoretical physics. Imagine a world where communication is truly unbreakable, where the very act of eavesdropping alerts the intended recipients. This is the promise of quantum cryptography, a field that harnesses the bizarre properties of entangled particles to create ultra-secure communication channels. In this quantum encrypted future, any attempt to intercept a message would inevitably disturb the delicate entangled state, immediately revealing the presence of an intruder. But the ramifications of quantum entanglement reach even further, touching upon the very nature of consciousness itself. Some theorists propose that the interconnectedness we observe at the quantum level might extend to our conscious experiences. Could the entangled states of particles reflect a deeper level of connectivity that underpins the very essence of awareness? This tantalizing possibility suggests that our individual consciousnesses might be more intimately linked than we ever imagined, forming a vast cosmic web of interconnected experiences. As we contemplate these mind-bending concepts, we begin to see how quantum entanglement might offer insights into the fundamental structure of the universe. Some physicists posit that the connections we observe between entangled particles could be a window into the hidden architecture of space-time itself. What if the fabric of reality is woven from threads of quantum entanglement, creating a cosmic tapestry more intricate and interconnected than we ever dared to dream? The exploration of quantum entanglement forces us to confront the limitations of our classical intuitions. In this strange quantum realm, causality becomes a fluid concept, and the very notion of separate objects existing in distinct locations begins to dissolve. We are compelled to consider a universe where everything is fundamentally connected, where the act of observation can instantaneously influence distant particles, and where the line between observer and observed blurs into a cosmic dance of interrelated phenomena. As we grapple with these concepts, we must remain open to the possibility that our current understanding is merely scratching the surface of a deeper, more fundamental reality. The quest to unravel the mysteries of quantum entanglement may lead us to revise our most basic assumptions about the nature of existence, consciousness, and the universe itself. 6. Cosmic maelstroms, the mystery of black holes. As we ponder the profound implications of quantum entanglement, our cosmic journey takes us to the edge of an even greater mystery. Picture a region of space so warped, so dense, that it forms a bottomless pit in the fabric of reality. What secrets might we uncover by peering into the abyss of a black hole? At the heart of every galaxy lurks a cosmic monster, a region where gravity reigns supreme with such intensity that not even light can escape its grasp. These enigmatic structures, known as black holes, represent the ultimate challenge to our understanding of physics. They are born from the remnants of massive stars that have exhausted their nuclear fuel, collapsing under their own gravitational pull to create a singularity of infinite density. The formation of a black hole marks a point of no return for matter and energy. As the gravitational field intensifies, it creates a boundary known as the event horizon. This invisible threshold serves as a cosmic point of no return, beyond which nothing can escape the black hole's gravitational clutches. Once any matter or information crosses this boundary, it is believed to be lost to the outside universe, raising profound questions about the nature of reality and information itself. Consider the implications of this cosmic prison. What happens to the information contained within objects that fall into a black hole? This question gives rise to the infamous information paradox, a conundrum that pits quantum mechanics against general relativity. Quantum theory insists that information cannot be destroyed, yet general relativity suggests that anything crossing the event horizon is lost forever. This fundamental contradiction challenges our most basic assumptions about the universe and pushes our understanding of physics to its limits. Imagine standing at the edge of an event horizon, peering into the abyss. The extreme warping of space-time near a black hole would create a surreal landscape where our intuitive understanding of physics breaks down. Time itself would slow to a crawl relative to distant observers, while space would twist and contort in ways that defy our earthbound experiences. In this cosmic maelstrom, the very fabric of reality unravels, revealing the deep connections between space, time, and gravity that Einstein's theory of general relativity so elegantly describes. But what lies beyond the event horizon, in the heart of a black hole? At the core, we encounter the singularity, a point where density becomes infinite and the laws of physics as we know them cease to apply. This represents a frontier of human knowledge, a place where our current understanding falters and new theories are desperately needed. Some speculate that Event Horizon Telescope recently captured the first direct image of a black hole's event horizon. This groundbreaking observation not only confirmed predictions made by general relativity, but also opened new avenues for exploring these cosmic enigmas. As we grapple with the profound implications of black holes, new theories emerge to reconcile the seemingly irreconcilable aspects of their nature. The holographic principle offers a tantalizing possibility. Perhaps all the information about what falls into a black hole is encoded on its event horizon, rather than being lost forever. This theory suggests that the surface area of the event horizon is proportional to the amount of information it contains, challenging our traditional notions of volume and information storage. Contemplate the cosmic tapestry woven by these gravitational titans. Black holes don't merely exist in isolation, they shape the very structure of our universe. Supermassive black holes at the centers of galaxies act as cosmic architects, influencing the formation and evolution of entire stellar neighborhoods. Their gravitational influence extends far beyond their event horizons, sculpting the cosmic web that connects galaxies across the vastness of space. As we stand at the precipice of discovery, gazing into the cosmic abyss, we find ourselves humbled by the magnitude of the unknown. Black holes represent not just a challenge to our understanding of physics, but an invitation to expand our cosmic perspective. They remind us that the universe is far stranger and more wondrous than we could have ever imagined, filled with phenomena that push the boundaries of our comprehension. 7. The cosmic tapestry, multiverse theory. As we gaze into the cosmic abyss, our minds stretching to comprehend the enigmatic nature of black holes, an even more perplexing question emerges. Could our universe be just one of many? Imagine a reality where every decision you've ever made spawns a new universe, a vast multiverse where every possibility, no matter how improbable, exists somewhere. This concept, known as the multiverse theory, challenges our understanding of reality itself, suggesting that our cosmos is but one bubble in an infinite sea of universes. The multiverse theory proposes a cosmic landscape so vast that it makes our universe seem like a single thread in an infinite cosmic weave. But how can we begin to comprehend such a notion? Let's explore the various forms this theory takes, each offering a unique perspective on the nature of existence. Consider Hugh Everett's many worlds. Interpretation of quantum mechanics. This theory suggests that every time a quantum event occurs, a particle decaying or a photon being emitted, the universe splits into multiple parallel versions of itself, accommodating all possible outcomes. Imagine for a moment the implications of this idea. In this branching tree of choices and events, there exist infinite versions of ourselves, making every possible decision in every conceivable way. How does this affect our understanding of free will and the consequences of our actions? Now, picture space as an inflating balloon with smaller bubbles forming within it. This is the concept of bubble universes, arising from inflation theory. In this model, the Big Bang is not a unique event, but a continuous process. Each bubble represents a separate universe with distinct physical properties, an idea proposed by physicists Alan Guth and Andre Linde. These bubbles, or patches of space, become their own universes, each with its own set of physical laws and dimensions. But the rabbit hole of multiverse theories goes even deeper. Max Tegmark's mathematical multiverse theory posits that all possible mathematical structures exist in their own universes. Imagine a vast library of universes, each defined by its own set of mathematical equations and physical laws. In this view, our reality is just one narrative in an infinite collection of cosmic stories, each with its own unique properties and possibilities. As we contemplate these mind-bending concepts, a profound question rises. Why does our universe appear so finely tuned for life? This is where the anthropic principle comes into play. It suggests that the conditions of the universe must allow for the observer's existence. In a multiverse with infinite variations, it's not surprising that some universes have conditions favorable for life. But this principle challenges our understanding of free will and identity. If our existence is contingent upon the specific laws of our universe, what does this mean for our sense of self and purpose? The implications of the multiverse for human existence are staggering. If every possible outcome occurs in separate universes, how do we define the meaning of our choices? Critics argue that if every decision leads to a branching universe, it could diminish the significance of our actions. Yet supporters contend that it simply expands the possibilities of existence, creating a cosmic tapestry of infinite potential. However, we must remember that the multiverse theory remains highly speculative. Proving its existence presents a significant challenge, as these other universes might be undetectable from our vantage point. Some scientists are exploring potential indirect evidence, such as gravitational waves or cosmic background radiation, that might show traces of interactions between our universe and others. But for now, the multiverse remains a tantalizing possibility, pushing the boundaries of our cosmic understanding. As we ponder these vast concepts, we're invited to imagine an endless tapestry of realities, each with its own unique version of physics, existence, and passive consciousness. Imagination. What if the fundamental building blocks of our universe aren't particles at all, but infinitesimal vibrating strings? This idea, as elegant as it is perplexing, promises to rewrite the very fabric of reality. String theory proposes a radical reimagining of the universe's most basic components. Instead of point-like particles, picture minuscule strings vibrating in complex patterns. Each unique vibrational mode corresponds to a different particle, an electron, a quark, or even the elusive graviton. It's as if the universe is a cosmic symphony, with each particle representing a distinct note in an intricate composition. But the true magic of string theory lies in its ambition to unify all forces of nature. For decades, physicists have sought a theory of everything, a single framework that could explain all fundamental interactions in the universe. String theory tantalizes us with this possibility, offering a path to reconcile the seemingly irreconcilable, quantum mechanics and general relativity. Consider the implications of this unification. In one elegant stroke, string theory smooths out the mathematical infinities and paradoxes that arise when we try to merge these two pillars of modern physics. By treating particles as one-dimensional strings rather than dimensionless points, it mitigates the inconsistencies that have long puzzled physicists. Yet, as we peel back the layers of string theory, we encounter a startling proposition. Our universe might harbor far more dimensions than we can perceive. While we navigate through 3 spatial dimensions and 1 of time, string theory suggests the existence of up to 7 additional dimensions. These extra dimensions, invisible to our senses, could be curled up so tightly that they remain undetectable at human scales. Imagine, for a moment, the profound implications of these hidden realms. How might they shape the fundamental nature of reality? Are they merely mathematical constructs, or do they represent physical spaces beyond our comprehension? The answers to these questions could revolutionize our understanding of the cosmos. As we grapple with the concept of extra dimensions, string theory introduces us to another mind-bending idea. Brains. These multi-dimensional objects expand our cosmic horizons even further. Picture our entire universe as a three-dimensional brain floating in a larger, multi-dimensional space. This framework, known as M-theory, connects the 5 different versions of string theory, offering a more comprehensive view of reality. The introduction of brains opens up new avenues for explaining cosmic mysteries. Could the gravitational effects we attribute to dark matter be the result of gravity leaking from a nearby brain? Might the Big Bang have been a collision between 2 cosmic brains? These questions, once relegated to the realm of science fiction, now find a home in cutting-edge theoretical physics. Yet, for all its theoretical elegance, string theory faces significant challenges. The strings themselves are incredibly small, far beyond the reach of our most advanced scientific instruments. The energy levels required to test string theory. Predictions dwarf our current technological capabilities. This lack of experimental verification has led some critics to argue that string theory risks becoming more of a philosophical or mathematical exercise than a physical theory. Moreover, the vast landscape of possible solutions, potentially as many as 10 power 500 different universes, complicates the identification of a unique solution that corresponds to our own universe. This abundance of possibilities raises profound questions about the nature of scientific theories and the limits of our ability to understand the cosmos. Despite these challenges, proponents of string theory remain undeterred. They argue that its mathematical consistency offers a framework for understanding the universe at a level that no other theory currently achieves. The theory's ability to naturally incorporate gravity by predicting the existence of the graviton particle is seen as a significant strength as we contemplate the hidden harmonies of strings and the potential existence of extra dimensions. We're invited to expand our conception of reality. String theory challenges us to think beyond the confines of our perceptible world, suggesting that the nature of existence may be far more varied and complex than we ever imagined. 9. The fabric of reality, quantum loop gravity. As we venture deeper into the quantum realm, we encounter a theory that challenges our most fundamental assumptions about the nature of reality itself. Imagine a universe where space and time are not the smooth, continuous entities we perceive, but rather a tapestry woven from discrete threads of quantum space-time. This is the world of quantum loop gravity, a theory that invites us to reconsider the very fabric of our cosmos. At its core, quantum loop gravity proposes a radical reimagining of space-time. Instead of a seamless continuum, picture a network of interconnected loops, forming what physicists call a spin network. This intricate structure serves as the scaffolding of space itself, with each loop representing a fundamental unit of space-time. It's as if reality is composed of indivisible atoms of space and time, much like matter is built from elementary particles. This concept challenges our intuitive understanding of the universe. We're accustomed to thinking of space as an empty stage upon which the drama of existence unfolds. But what if the stage itself is an active participant, constantly shifting and evolving? In quantum loop gravity, geometry becomes a dynamic entity, capable of change and evolution. The shape of space itself can transform. This quantization of time forces us to reconsider the nature of causality and the arrow of time itself. How might our perception of past, present, and future change if we could perceive these quantum leaps of time? One of the most intriguing aspects of quantum loop gravity is its potential to resolve long-standing paradoxes in physics. Take, for example, the problem of singularities, points of infinite density predicted by general relativity, such as those thought to exist at the center of black holes, or at the moment of the Big Bang. These infinities have long troubled physicists as they suggest a breakdown of our physical laws. Quantum loop gravity offers a solution by eliminating these singularities altogether. In the realm of black holes, this theory paints a fascinating picture. Instead of an infinitely dense point at the center, quantum loop gravity suggests a more complex structure where space-time itself becomes highly curved but remains finite. This could revolutionize our understanding of these cosmic enigmas, potentially resolving the information paradox that has puzzled scientists for decades. Perhaps even more profound are the implications for the origin of our universe. Rather than a singular Big Bang, quantum loop gravity predicts what physicists call a big bounce. Imagine the universe undergoing cycles of contraction and expansion, with each bounce giving birth to a new cosmic epoch. This cyclic model of the universe challenges linear notions of cosmic history and opens up mind-bending possibilities about the nature of existence itself. As we contemplate these ideas, it's natural to draw comparisons with other theories of quantum gravity, such as string theory. While both seek to reconcile quantum mechanics with gravity, their approaches differ significantly. String theory posits that fundamental particles are actually tiny vibrating strings in multiple dimensions. Quantum loop gravity, on the other hand, focuses on quantizing space-time itself, treating it as the fundamental entity from which all else emerges. This distinction leads to fascinating questions about the nature of reality. Are the fundamental building blocks of the universe vibrating strings or quantized loops of space-time? Or is there perhaps a deeper truth that unifies these perspectives? As we stand at the frontier of theoretical physics, these questions remind us of the vast unknown that still lies before us. The pursuit of quantum loop gravity represents a bold step into uncharted territory. It offers a framework for understanding the quantum properties of gravity, potentially unveiling insights into the deepest mysteries of our universe. From the birth of cosmic structures to the ultimate fate of black holes, this theory promises to reshape our cosmic perspective, yet we must temper our excitement with scientific caution. Quantum loop gravity, like many theories in cutting-edge physics, remains speculative. It lacks direct experimental evidence, and the challenges of testing its predictions at the minute scales it describes are formidable. The theory continues to evolve as physicists refine its mathematical foundations and explore its consequences. 10. The Holy Grail in search of a theory of everything. As we step back from the intricate loops of quantum space-time, a grander question emerges. What if there exists a single, elegant equation that could describe every aspect of our universe, from the tiniest quark to the largest galaxy cluster? This tantalizing possibility beckons us towards the ultimate pursuit in physics. The theory of everything, the quest for a theory of everything, TOE, represents humanity's deepest yearning to comprehend the nature of existence itself. It's an ambitious attempt to unify all fundamental forces and particles in the universe under a single theoretical framework. Imagine a cosmic tapestry where gravity, electromagnetism, and the strong and weak nuclear forces are woven together with exquisite precision, revealing the hidden patterns that govern reality. At the heart of this pursuit lies a fundamental challenge. How do we reconcile the vast cosmic scales described by general relativity with the bizarre quantum realm of subatomic particles? These two pillars of modern physics, while immensely successful in their respective domains, seem to speak different languages when it comes to describing the universe as a whole. The journey towards a unified theory has been paved by brilliant minds throughout history. Consider Albert Einstein, who, after revolutionizing our understanding of gravity with general relativity, spent decades struggling to find a framework that could elegantly describe electromagnetism in the same way. His quest, while ultimately unfulfilled, laid the groundwork for future generations of physicists to build upon. As we moved into the mid-20th century, a new generation of thinkers like Richard Feynman and Steven Weinberg advanced quantum field theory, successfully combining electromagnetism with the weak and strong forces into what we now call the standard model of particle physics. This remarkable achievement brought us closer to the dream of unification, but a crucial piece of the puzzle remained elusive: gravity. The incorporation of gravity into a unified framework continues to be one of the greatest challenges in theoretical physics. It's as if we're trying to solve a cosmic jigsaw puzzle, where the piece representing gravity seems to belong to an entirely different set. This enigma has sparked the development of various candidate theories, each offering a unique perspective on the nature of reality. String theory, for instance, proposes that the fundamental building blocks of the that space-time itself is quantized, composed of tiny loops that form a vast, intricate network. This theory provides an alternative route to understanding gravity at the quantum level, painting a picture of reality where space and time emerge from more fundamental quantum processes. As we contemplate these grand theories, we're led to profound philosophical questions about the nature of existence. If we were to discover a true theory of everything, how would it reshape our understanding of concepts like causality, free will, and the very fabric of reality? Would such a theory reveal an underlying simplicity to the universe, or might it uncover even greater complexities that challenge our current notions of comprehension? The pursuit of a theory of everything is not merely an academic endeavor. It embodies humanity's unyielding curiosity and our desire to understand not just how the universe works, but why it exists at all. It's a cosmic detective story where each clue we uncover leads to new mysteries, pushing the boundaries of human knowledge to their ultimate limit. Yet, as we stand on the precipice of potentially revolutionary discoveries, we must also consider the possibility that a complete theory of everything might forever elude us. Some physicists caution that the universe's complexity may never be fully captured by a single theory. Perhaps the very act of observation limits our ability to grasp the totality of existence, or maybe the true nature of reality is simply beyond the reach of human comprehension. Despite these challenges, the journey towards understanding the universe is as significant as the destination itself. Each step taken in this pursuit deepens our knowledge and unveils new facets of the cosmic tapestry we inhabit. The search for a theory of everything pushes us to the very limits of human ingenuity, forcing us to question our most fundamental assumptions about reality. 11. The cosmic accelerator, dark energy, and the fate of the universe. Just when we thought we were approaching a comprehensive understanding of the cosmos, the universe threw us a cosmic curveball. Picture an invisible force, omnipresent yet undetectable, pushing galaxies apart at an ever-increasing rate. This enigmatic phenomenon, known as dark energy, challenges everything we thought we knew about the nature of reality and the fate of our universe. The story of dark energy began in the late 1990s when astronomers made a startling discovery. By observing distant supernovae, they found that the universe's expansion wasn't slowing down as expected. Instead, it was accelerating. This observation shattered our previous understanding of cosmic evolution and gave birth to one of the most perplexing mysteries in modern physics. Consider the implications of this discovery. We've long understood gravity as the dominant force shaping the large-scale structure of the universe. It pulls matter together, forming galaxies, stars, and planets. But now we're faced with a force that seems to counteract gravity on the grandest scales. It's as if the cosmic stage itself is expanding, pushing everything apart with increasing vigor. To explain this accelerating expansion, physicists have proposed various theories. One of the leading contenders is the cosmological constant, an idea originally introduced by Albert Einstein. Imagine space itself possessing an intrinsic energy density, uniform throughout the cosmos. This energy, constant and unchanging, could drive the expansion we observe. It's a simple and elegant solution, but it raises profound questions about the nature of empty space. Another intriguing possibility is the concept of quintessence. Unlike the cosmological constant, quintessence proposes that dark energy is dynamic, changing over time and space. Picture a cosmic field permeating the universe, its energy density fluctuating as the cosmos evolves. This theory offers more flexibility in explaining the observed acceleration, but it also introduces new complexities and challenges to our understanding. Recent studies have unveiled an even more mind-bending possibility. What if dark energy is related to the vacuum energy predicted by quantum field theory? This connection suggests that even the emptiest of spaces is teeming with energy, a consequence of the quantum fluctuations that occur at the smallest scales of reality. It's a concept that bridges the vast expanse of the cosmos with the bizarre realm of quantum mechanics, hinting at a deeper unity in the laws of nature. As we contemplate the nature of dark energy, we must also confront its implications for the ultimate fate of our universe. If dark energy continues to dominate, we might be headed for a big freeze. Imagine a cosmos where galaxies drift ever further apart, stars burn out, and the night sky grows increasingly dark and empty. It's a chilling vision of cosmic loneliness, where the very fabric of space-time stretches into an infinite, cold expanse. But the story doesn't end there. Some theories suggest that dark energy might not be constant. If its nature or strength were to change, the cosmic story could take a dramatic turn. Consider the possibility of a big rip, where the acceleration becomes so intense that it tears apart not just galaxies and stars, but the very atoms that compose them. It's a scenario that pushes our understanding of physics to its limits and beyond. The quest to understand dark energy intersects with some of the most cutting-edge areas of physics. String theory, with its vision of a universe composed of vibrating, multidimensional strings, might offer insights into the nature of this mysterious force. Quantum gravity, the holy grail of theoretical physics that seeks to reconcile quantum mechanics and general In the grand tapestry of existence, the vast and the intimate are woven together in ways we're only beginning to comprehend. 12. The invisible scaffold, dark matter and cosmic structure. As we drift from the expansive force of dark energy, we encounter an equally perplexing cosmic enigma. What if the majority of matter in our universe is invisible, shaping galaxies like an unseen sculptor's hand? Welcome to the realm of dark matter, where the cosmic landscape is molded by forces beyond our perception. Imagine a universe where what we see is merely the tip of the cosmic iceberg. As your consciousness floats between wakefulness and sleep, consider this: approximately 27% of the universe's mass is composed of a substance that neither emits, absorbs, nor reflects light. This invisible matter, detectable only through its gravitational effects, forms the hidden scaffolding of our cosmos. The evidence for dark matter's existence emerges from a tapestry of astronomical observations. Picture a spiral galaxy, its stars spinning in a cosmic dance. Now consider the outer edges of this galactic disk. According to the laws of gravity and our understanding of visible matter, these distant stars should rotate more slowly than those closer to the center. Yet astronomers observe a curious phenomenon. Stars at the galaxy's periphery rotate at much higher speeds than expected based on visible mass alone. This discrepancy hints at the presence of an unseen gravitational influence, dark matter. As we ponder the nature of this elusive substance, our minds wander to the realm of particle physics. What could constitute this invisible cosmic architecture? Scientists propose various candidates, each with its own unique properties. Imagine particles called weakly interacting massive particles, or WIMPs, heavy entities that interact through the weak nuclear force. Or consider axions, lightweight particles proposed to solve a different mystery in quantum chromodynamics. These hypothetical particles, like shy actors in a cosmic play, refuse to step into the spotlight of our detectors. The quest to unmask dark matter has led to a variety of ingenious detection efforts. Picture underground laboratories where cryogenic detectors wait patiently for the rare interaction between a dark matter particle and normal matter. Envision noble gas-time projection chambers, their sensitive instruments poised to capture the faintest whisper of a dark matter encounter. These experiments, like cosmic fishing expeditions, cast their nets into the sea of the unknown, hoping to catch a glimpse of the universe's hidden bounty. As we delve deeper into the nature of dark matter, its role in shaping the cosmic landscape becomes increasingly apparent. Imagine the universe as a vast construction site, with dark matter serving as the invisible framework upon which visible matter builds its structures. Recent advancements suggest that dark matter acts as a cosmic scaffolding, influencing the distribution and movement of galaxies within the intricate web of the cosmos. Like the hidden support beams in your bedroom walls, dark matter provides the unseen structure that allows the visible universe to take shape. The study of dark matter transcends the boundaries of astronomy, reaching into the heart of particle physics. As we explore this cosmic mystery, we find ourselves at the intersection of the infinitely large and the infinitesimally small. The search for dark matter particles pushes the boundaries of our understanding of fundamental forces, challenging our notions of the universe's basic building blocks. Each new discovery in dark matter research has the potential to reshape our understanding of the cosmos, much like how the discovery of a new fundamental particle can rewrite the laws of physics. As your mind drifts closer to the realm of dreams, consider how dark matter might connect to other cosmic enigmas. The matter-antimatter asymmetry in the universe, for instance, remains a perplexing puzzle. Why does our universe contain more matter than antimatter? Could the properties of dark matter hold the key to this cosmic imbalance? As we explore these connections, we begin to see the universe as an intricate tapestry where pulling on one thread reveals unexpected patterns in seemingly unrelated areas. 13. The quantum foam, vacuum fluctuations, and virtual particles. As we drift closer to the quantum realm, our perception of reality begins to unravel. Imagine the emptiest region of space you can conceive, a void so vast and barren that even atoms seem like bustling metropolises in comparison. Now let's zoom in, peering deeper into this apparent nothingness. What we discover challenges our very notion of emptiness itself. At the quantum scale, this vacuum is anything but empty, is a frothing sea of activity, a cosmic dance of virtual particles that pop in and out of existence faster than thought. This is the quantum foam, a concept that turns our understanding of nothingness on its head. In quantum field theory, even the vacuum, what we typically consider empty space, is teeming with energy and possibility. Consider the implications of this quantum foam. Every cubic centimeter of seemingly empty space is alive with fluctuations, borrowing energy from the vacuum itself to manifest fleeting particles. These virtual particles are not mere mathematical constructs, but have measurable effects on our physical world. They challenge our classical intuitions, revealing a universe where the very fabric The restricted space between the plates suppresses certain vacuum fluctuations, creating an imbalance in the quantum field. This imbalance results in a net force, pushing the plates together, a ghostly touch from the quantum realm. The concept of vacuum energy intrinsically linked to these fluctuations has profound implications for cosmology. It plays a crucial role in our understanding of the universe's expansion and evolution. Yet it also presents us with one of the most perplexing puzzles in modern physics, the cosmological constant problem. Theoretical predictions of vacuum energy density vastly differ from observational evidence, creating a discrepancy that spans many orders of magnitude. This enigma stands as a testament to the depths of our ignorance. a humbling reminder that even in the seeming simplicity of empty space, the universe holds secrets beyond our current comprehension. As we ponder these quantum fluctuations, let's consider their potential role in one of the most mysterious phenomena in the cosmos: black holes. Stephen Hawking proposed that these vacuum fluctuations might be the key to understanding how black holes evaporate over time. Near the event horizon, virtual particle pairs can be torn apart by the intense gravitational field. One particle falls into the black hole, while the other escapes into space, appearing to an outside observer as radiation emanating from the black hole. This process, known as Hawking radiation, connects the quantum foam to the grand cosmic scales of general relativity, hinting at a deeper unity in physics that we've yet to fully grasp. The implications of understanding vacuum fluctuations extend beyond pure theory. They tantalize us with the possibility of harnessing the energy of the vacuum itself. Imagine tapping into this cosmic reservoir, drawing power from the very fabric of space-time. While such technologies remain firmly in the realm of speculation, they illustrate how exploring the quantum foam could lead to revolutionary breakthroughs in energy production and manipulation. As we contemplate these mind-bending concepts, we're forced to confront the limitations of our intuitive understanding of reality. The quantum foam reveals a universe far stranger and more dynamic than we ever imagined. It challenges us to reconsider what we mean by empty and full, blurring the lines between existence and non-existence. 14. The cosmic hologram, information and reality. As we contemplate the blurred lines between existence and non-existence, let's consider an even more perplexing possibility. What if the very fabric of reality we perceive is merely a projection, a cosmic illusion cast upon the walls of our universe? The holographic principle suggests a truth so startling, it makes the quantum foam seem almost conventional by comparison. Imagine for a moment that everything you know, your thoughts, memories, and the vast expanse of the cosmos itself could be encoded on the surface of your bedroom walls. This isn't science fiction, but a profound implication of the holographic principle, a concept that challenges our most fundamental assumptions about the nature of reality and information. The holographic principle emerged from the study of black holes, those cosmic enigmas where the laws of physics as we know them break down. Physicists discovered a curious property of these celestial objects. The entropy of a black hole, a measure of its information content, is proportional to the area of its event horizon rather than its volume. This seemingly innocuous observation sparked a revolution in our understanding of space, time, and information. Leonard Susskind and others expanded on this idea, proposing that what applies to black holes might apply to the entire universe. In essence, they suggested that our three-dimensional reality could be a projection from a lower dimensional surface, much like a hologram. This mind-bending concept implies that everything we perceive, from the chair you're sitting on to the farthest galaxies, might be a holographic representation of information encoded on a cosmic boundary. Consider the implications of this principle for our understanding of quantum gravity. That elusive theory that aims to reconcile the microscopic world of quantum mechanics with the cosmic scale of general relativity. The holographic principle suggests that space and time themselves may not be fundamental aspects of reality, but rather emergent properties arising from more basic information encoded on a two-dimensional surface. In other words, the very stage upon which the drama of existence unfolds might be an illusion, a holographic projection from a simpler, more fundamental reality. This principle offers a tantalizing solution to one of the most vexing problems in modern physics, the information paradox associated with black holes. When matter falls into a black hole, where does the information describing its quantum state go? Does it vanish forever, violating the principles of quantum mechanics? The holographic principle proposes that this information isn't lost at all, but rather encoded on the event horizon itself, preserving the unitarity of quantum mechanics and resolving the paradox. The holographic principle finds a natural home in string theory, where it emerges as a feature of the theory rather than an ad hoc addition. In the framework of string theory, where the fundamental constituents of the universe are not point-like particles, but tiny vibrating strings, the idea of the universe as a holographic projection seems less far-fetched. This convergence of ideas from different branches of theoretical physics lends credence to the holographic principle and What does that mean for our understanding of consciousness, free will, and the nature of itself? Are we too just holographic projections of information encoded elsewhere? Recent research has provided tantalizing hints of holographic duality in simple models of quantum entanglement, offering indirect support for the holographic principle. These findings suggest that this principle may play a crucial role in understanding the behavior of quantum systems, potentially bridging the gap between the quantum and classical worlds. Imagine looking at your reflection in a broken mirror. Each shard contains a complete image of your face, albeit from a slightly different angle. In a similar way, the holographic principle suggests that each fragment of our universe contains information about the whole. This fractal-like nature of reality implies a deep interconnectedness that transcends our usual notions of space and time. 15. The hidden harmony, symmetry in physics. As we transition from the fractal-like interconnectedness of the holographic universe, let's consider another profound pattern woven into the fabric of reality. Imagine a universe where the most fundamental laws of nature arise not from chaos, but from an exquisite balance, a cosmic dance choreographed by an invisible principle of perfect harmony. This is the realm of symmetry in physics, a concept so powerful it might hold the key to unlocking the universe's deepest secrets. Symmetry in physics goes far beyond the simple mirror reflections we observe in everyday life. It's a mathematical principle that governs the behavior of particles and forces at the most fundamental level. Consider the conservation laws that underpin our understanding of the physical world. The conservation of energy, for instance, isn't just a convenient rule. It's a direct consequence of the symmetry of time. In other words, the laws of physics remain unchanged whether we perform an experiment today, tomorrow, or a million years from now. But the influence of symmetry extends even further. The very forces that shape our universe, gravity, electromagnetism, and the nuclear forces, may owe their existence to a process of symmetry breaking. Picture the early universe, a place of perfect uniformity and balance. As this primordial state cooled and expanded, these symmetries began to break, like cracks forming in a perfect sheet of ice. From these cracks emerged the distinct forces we observe today, each with its own unique properties and behaviors. The quest to understand symmetry has led physicists to propose even more exotic concepts. Supersymmetry, for instance, suggests a profound connection between two fundamental types of particles, bosons and fermions. Imagine a cosmic mirror that not only reflects what we see, but transforms matter into force and vice versa. If proven true, supersymmetry could provide a unified description of all fundamental particles and forces, bringing us one step closer to the elusive theory of everything. But why should the universe care about symmetry at all? The answer might lie in the deep connection between symmetry and beauty that we observe not just in physics, but in art and nature as well. The same principles that govern the behavior of subatomic particles also manifest in the spiral of a nautilus shell, the hexagonal cells of a honeycomb, or the fractal patterns of a snowflake. This suggests that beauty and harmony might be more than just human constructs. They could be intrinsic to the very fabric of reality. The power of symmetry extends beyond mere description. It serves as a guiding principle in the search for new particles and forces. At particle accelerators like the Large Hadron Collider, physicists design experiments based on predictions made by symmetry-based theories. They seek to uncover hidden symmetries or observe the consequences of symmetry, breaking at ever higher energies. Each discovery, or lack thereof, refines our understanding of the universe's underlying structure. As we contemplate the role of symmetry in physics, we're led to profound philosophical questions. If the most fundamental laws of nature arise from perfect balance, what does this say about the nature of existence itself? Are we living in a universe that inherently tends towards harmony and order, despite the apparent chaos we often observe? Consider the implications of a universe governed by symmetry. Every conservation law, every fundamental force, every particle and interaction might be a manifestation of this deeper principle. The electrons orbiting atomic nuclei, the planets circling stars, and the galaxies spinning through the cosmos all might be engaged in an intricate ballet, their movements dictated by the hidden symmetries of space and time. Yet, paradoxically, it's often the breaking of symmetry that gives rise to the complexity and diversity we observe in the universe. Perfect symmetry would result in a uniform, featureless cosmos. It's the subtle imperfections, the slight imbalances, that allow for the formation of stars, planets, and ultimately, life itself. In this light, we might view the entire history of the universe as a grand unfolding of broken symmetries, each imperfection giving rise to new structures and possibilities. 16. The cosmic mind, consciousness, and the universe. As we gaze into the cosmic mirror, we encounter a reflection that challenges our very understanding of existence. What if the universe isn't just a vast expanse of matter and energy, but a canvas painted with the brush strokes of consciousness itself? This profound question beckons us to explore the frontier, where physics and philosophy intertwine, where the observer and the observed become one. Consider for a moment the concept that invites us to But it's the strong anthropic principle that truly ignites our imagination, proposing that the universe must have properties that allow life to develop. This perspective challenges us to reconsider the role of consciousness in the grand tapestry of reality. Are we merely fortunate accidents in an indifferent cosmos, or are we integral to its very structure? The strong anthropic principle hints at a universe that isn't just hospitable to life and consciousness, but perhaps fundamentally intertwined with it. As we venture deeper into this cosmic enigma, we encounter the concept of integrated information theory. This framework proposes that consciousness isn't an emergent property of complex brains, but a fundamental aspect of reality itself. It suggests that consciousness corresponds to a system's capacity to integrate information. Imagine the universe as a vast network of interconnected nodes, each possessing a degree of consciousness proportional to its ability to process and unify information. In this view, our human consciousness isn't unique in kind, but in degree, a particularly complex manifestation of a property inherent to the cosmos itself. But how does this perspective align with our understanding of physics? The quantum realm, with its emphasis on observation and measurement, has long hinted at a peculiar relationship between consciousness and reality. The act of observation seems to collapse the wave function, determining the state of a particle. This has led some to speculate about a deeper connection between mind and matter, suggesting that consciousness might play a more fundamental role in shaping reality than we previously thought. As we ponder these ideas, we're drawn to even more speculative realms. Consider the concept of panpsychism, which proposes that consciousness is a fundamental feature of all matter. In this view, even the smallest particles possess a form of proto-consciousness, which combines and integrates to form the complex awareness we experience. This idea challenges our traditional notions of mind and matter, suggesting that the divide between the two might be more illusory than we imagined. But perhaps the most awe-inspiring perspective comes from Pierre Teilhard de Chardin's omega point theory. This visionary concept envisions the universe as evolving towards a final state of supreme complexity and consciousness. Imagine a cosmos not just expanding in space, but growing in awareness, moving inexorably towards a singularity of divine love. and knowledge. This theory merges scientific thought with philosophical and theological perspectives, presenting a dynamic view of the universe where consciousness isn't just an observer, but an active participant in cosmic evolution. Teilhard believed that consciousness is woven into the very fabric of the universe, evolving from simple awareness to increasingly complex forms. In this light, our individual experiences contribute to a greater, collective consciousness, a cosmic mind gradually awakening to itself. This perspective challenges us to see our role in the universe not as passive observers, but as crucial participants in a grand cosmic drama. As we contemplate these ideas, we're forced to confront the hard problem of consciousness, the challenge of explaining how subjective experiences arise from physical processes. This problem has long puzzled philosophers and scientists alike, resisting easy explanations within our current scientific framework. Yet, by considering consciousness as fundamental rather than emergent, we open new avenues for understanding this deep mystery. The implications of these theories are profound, stretching far beyond academic discourse. If consciousness is indeed fundamental to the universe, it transforms our understanding of reality, purpose, and our place in the cosmos. It suggests a universe that is not just alive with energy and matter, but with meaning and intention. 17. The eternal return, cycles of the cosmos. As we contemplate a universe alive with meaning, let us turn our gaze to an even grander vista of cosmic existence. What if our universe, vast as it may be, is but a single breath in an endless cycle of cosmic rebirth? Imagine a reality where the very fabric of space and time folds and unfolds eternally, each cycle birthing a new cosmos from the ashes of the old. This concept of a cyclic universe challenges our linear perception of cosmic history. Rather than a singular Big Bang event marking the birth of all existence, cyclic models propose that the universe undergoes infinite cycles of expansion and contraction. It's a notion that echoes through the corridors of time, resonating with ancient philosophies such as Hindu cosmology, which describes the universe as undergoing endless cycles of creation, preservation, and destruction. Consider the ekpyrotic scenario, a prominent cyclic model that paints a picture of cosmic genesis unlike any other. In this theory, our universe emerges not from a point of infinite density, but from the collision of two three-dimensional branes, vast membranes existing in a higher dimensional space. This cosmic collision ignites a new cycle of expansion, a fresh canvas upon which the laws of physics can paint the intricate tapestry of galaxies, stars, and life itself. But why entertain such a radical departure from the standard cosmological model? The answer lies in the puzzles that continue to perplex cosmologists. The nature of the Big Bang singularity, that point of infinite density that defies our current understanding of physics, remains a thorn in the Each exhale is an expansion, spreading matter and energy across vast expanses. Each inhale is a contraction, drawing the cosmos back towards unity. This rhythm, playing out on a scale beyond imagination, mirrors the very essence of life, a constant cycle of renewal and transformation. The philosophical implications of an eternally recurring universe are profound. If the cosmos is indeed cyclical, how might this reshape our understanding of time, causality, and the very nature of existence? The concept challenges our notion of linear progress, suggesting instead a circular view of reality where endings become beginnings and destruction paves the way for creation. This cosmic dance of renewal intersects with cutting-edge theories in physics, string theory, and quantum gravity. In their quest to unify the fundamental forces of nature, provide fertile ground for cyclic models to take root. These theories suggest that the fundamental structure of the universe may be influenced by higher dimensions and the interactions of brains, potentially opening new avenues to understand the mechanisms behind cosmic cycles. Consider how these cycles might resolve paradoxes in our understanding of time and causality. In a universe that eternally recurs, the arrow of time becomes a circle. Cause and effect, typically viewed as a linear progression, could form a loop where every end is a new beginning. This cyclical nature might explain the origin of time itself, traditionally a stumbling block for cosmological theories that struggle to define what came before the Big Bang. As we ponder these grand cosmic cycles, let us not forget the rhythms that govern our own existence. The ebb and flow of the tides, the turning of the seasons, and even the cycles of sleep and wakefulness that punctuate our daily lives, all these mirror, in their own way, the grander cycles of the cosmos. Just as the universe may undergo periods of activity and rest, so too do we cycle between consciousness and unconsciousness, between the vivid realities of our waking hours and the mysterious realms of our dreams. 18. The cosmic perspective, our place in the universe. As we gaze into the infinite expanse above, a paradox emerges that challenges our very understanding of existence. How can being so small on a planet so seemingly insignificant dare to unravel the mysteries of a universe so vast? The answer, it turns out, may reshape our entire cosmic perspective. Our journey through the landscapes of modern physics has led us to this moment of profound reflection. We've explored the dance of particles in the quantum realm, witnessed the bending of space-time near massive celestial bodies, and contemplated the possibility of multiple universes. Yet, as we stand on our pale blue dot, we find ourselves face to face with a question that transcends the equations and theories we've encountered. What is our true place in this cosmic tapestry? The history of human thought is marked by a gradual shift in our cosmic perspective. We've moved from believing ourselves to be at the center of creation to recognizing our planet as but one of billions orbiting billions of stars in billions of galaxies. This journey of understanding has been humbling, to say the least. The sheer scale of the cosmos dwarfs our everyday concerns, making our individual lives seem almost inconsequential in comparison. But perhaps this apparent insignificance is merely an illusion, born from our limited perception. Consider for a moment the unique position we occupy in the universe. We are, as far as we know, the only beings capable of contemplating the cosmos and striving to understand its nature. Our consciousness, that ineffable quality that allows us to ponder our own existence, may be the universe's way of knowing itself. The quest to understand the universe is not merely an academic pursuit. It reflects fundamental aspects of human nature. Our curiosity, our sense of wonder, and our search for meaning drive us to explore the cosmos and our place within it. This relentless pursuit of knowledge has led us to discoveries that have transformed our understanding of reality itself. Imagine, for instance, the implications of the multiverse theory, the idea that our universe might be just one of many challenges our very notion of existence. It suggests that there could be infinite variations of reality, each with its own laws of physics. In this vast sea of possibilities, our universe, the one that gave rise to our consciousness, becomes both infinitely precious and fascinatingly arbitrary. The search for a theory of everything, a unified framework that could explain all fundamental forces and particles, embodies humanity's desire to comprehend the nature of existence itself. This quest prompts profound philosophical inquiries about free will, agency, and the underlying simplicity or complexity of the universe. As we edge closer to such a theory, we find ourselves grappling with questions that blur the lines between physics and philosophy. Our cosmic perspective also influences how we approach earthly challenges and our sense of shared humanity. When we view Earth from space, we see no borders, no nations, only a fragile blue sphere suspended in the void. This view has inspired many to advocate for global cooperation in addressing issues that affect us all, from climate change to resource management. Our understanding of the cosmos reminds us that we are all citizens of the same planet, sharing a common destiny. As we reflect on our cosmic perspective, we are reminded that as we journey through the cosmic tapestry of existence, our minds become vessels for the universe's introspection. Consider the possibility that each of us represents a unique vantage point through which the cosmos observes itself, our consciousness a mirror reflecting the grand design of reality. In the words of physicist Alan Watts, "You are the universe experiencing itself." This profound realization invites us to ponder our place in the cosmic order, not as mere spectators, but as active participants in the unfolding drama of existence. As we drift towards the realm of dreams, let us remember that our quest for understanding is as infinite as the cosmos itself. The pursuit of knowledge, like the expansion of the universe, knows no bounds. Richard Feynman, the renowned physicist, once encouraged us with these words: "The important thing is not to stop questioning. Curiosity has its own reason for existence." In this spirit, we continue our exploration, even as we close our eyes, allowing our subconscious to dance with the mysteries of the universe in the ethereal realm of sleep.